Hi guys, in this lecture we will be starting our study about the power electronics. So basically the course of power electronics has been divided into some units. First unit is power semiconductor devices. Second unit is rectifiers. Third unit is choppers. Then inverters, and then AC voltage controllers. Now in this year course, AC voltage controller does not appear in the GATE course. So we will be focusing our attention mainly on the first four concepts, that is power semiconductor devices, rectifiers, choppers and inverters. The recommended book for this topic is P.S. Bhimra. It consists of good theory as well as some numerical examples and unsolved problems. So you can go through that. Otherwise, the question bank that has been provided to you contains selected questions which are very good for your practice. So now let us get started with our power electronics course. So in this lecture what we will do is, we will first take a look at the basics of power electronics or prerequisites of power electronics. Now first question that comes to mind is, what is power electronics? Now if you see in our electrical engineering branch, what are the major subjects? First one is your electrical machines. Now what does electrical machine deal with? It deals with electromechanical power conversion, that is conversion of electrical energy into mechanical and vice versa. Then the next subject is power system. Now power system deals with generation, transmission and distribution of electrical energy. And then it is power electronics. In power electronics what we study is, we study about the conditioning and control of the electrical power. That is, we will say that power remains constant, but we wish to change the voltage, current, frequency and form that is AC or DC. Even if the power remains constant, that is, it does not amplify or attenuate the power, then also I want to change certain parameters like the level of the voltage, amplitude, frequency of the voltage, or even change the form whether from AC to DC or from DC to AC. That is done by means of power electronics circuit. Now power electronics branch is the most advanced subject in our electrical engineering, and most of the research goes on in the power electronics. What is the research all about is, the research is to develop power electronic converters which have high efficiency and yet they operate at a lower cost, and they must have high rating. Now there are two branches of electronics. One is your signal electronics, other is your power electronics. Signal electronics basically deals with your analog electronics and digital electronics. Now signal electronics has usually voltage level plus minus 15 volt, which is the supply voltage for op amp. Here the voltage in power electronics is in the order of kilovolts. Okay, and then here the current is from microampere to milliampere. Here the current is from ampere to kiloampere. Here power is from milliwatt to watt. Here power is from watt to kilowatt. That means power electronic devices, they only have the higher rating as compared to their signal electronic counterparts. That is, a diode will have a counterpart in the power electronics which is your power diode, and the difference between a signal diode and a power diode will be, power diode will possess much higher rating as compared to your signal diode. So power electronics is nothing but application of the electronics principle, the principles that we study in analog electronics, to the power domain. Okay, power domain means using the electronic equipments at much higher rating. That is the basics of the power electronics, and that is what is the necessity of the power electronics. Now here we have taken an example of a power electronic circuit. So this is a source which will be a machine. It will generate electrical power. Then there will be power processing circuit which will control the voltage and the frequency of this output, and then we will deliver it to the load. But now if you are controlling the power, then always closed loop control systems are more accurate as compared to your open loop. So we need certain feedback which is implemented in terms of this control circuit. So this control circuit does what is, it measures the load parameters and then it controls the switching of the power processing circuit. What is meant by switching of the power processing circuit is, this power processing circuit is made of different type of switches. So this control circuit will control the state of different switches, which switch will be on and which switch will be off, based on the parameters at the load side. Okay, so that is how different power electronic converters are implemented, and some of the power semiconductor devices are thyristor, power diode, power BJT, etc. Okay, so whatever devices have their signal counterparts, they will be associated with one additional term, that is power. Diode will become power diode, BJT will become power BJT. Now it is clear to me that I want to change the frequency, I want to change the voltage level. But what the question that comes to mind is, why do I want to do so? Though this question might seem silly, but it actually necessitates the application of the power electronics. What is the application of power electronics in our real world scenario? Now, first is, if you can control the voltage and frequency of the output of any system, then that system can be used to drive a DC or a AC motor. Now suppose I change the frequency, then synchronous speed changes 120 into F by P. If synchronous speed changes, then the speed of induction motor will change. If we have somehow variable frequency, it will have variable ns, and hence nr will be variable, which is equal to ns into 1 minus s. So that means we can control the speed of induction motor by varying the frequency using power electronic converters. Similarly, variable VDC can cause variable speed in case of DC motor. Okay, to control the DC motor, one of the methods is armature voltage control method, and in armature voltage control we control the terminal voltage of the DC motor. That can be controlled by the use of power electronic devices. Okay, and in the DC motor and the induction motor, usually induction motor is cheaper as compared to your DC motor, and its maintenance is easy. But the methods involved in controlling the speed of induction motor are more complicated as compared to the methods involved for the DC motor, because in DC motor if you change the supply voltage, it will change the speed. But in induction motor there are techniques like pole changing technique, variable frequency drive, such sort of techniques, so it is more difficult. So that is one application in terms of electrical machine. Next application comes with regards to the power system. Now what is the application in power system? It is used for reactive power compensation. That is, it can generate reactive power by means of devices like thyristor controlled reactor, thyristor switched capacitor, and static compensator. These will supply reactive power which can control the voltage at any bus. And SVC is also an example of power electronic applications. And when we studied power systems, then what we do is, there we apply SVC to clamp the voltage at any bus as well as improve the stability of the system. We saw that Pmax became 2 times Pmax initial. Okay, that is in the case for the power systems. Is it fine? These devices are called as FACTS devices, that is flexible AC transmission system. Because if you want to change the power carrying capability of AC, then we make use of these devices which can change the value of Pmax and hence the power capability of AC. Next application comes in transportation. In transportation also we use electrical motors, like in traction we use DC series motor, and in many railway cars we use induction motor. There, to control the speed, we can make use of the power electronic converters. Then low power application. If you want to control the speed of the fan, then fan also consists of a single phase induction motor. Then that means we can control the speed of fan by means of power electronic converters, because they can help us in controlling the speed of induction motor. And the last is renewable sources. Now renewable energy sources like solar cell and solar panel, they generate the DC power, but the power required for utilization is usually in the form of AC. So the conversion from DC to AC is done by means of power electronic converters. So these are many applications of the power electronic converters. That is why it is an interest area of the research. Now, what are the advantages of using power electronic converters than the conventional method of power conversion? First thing is no rotational loss. Power electronic devices are always static in nature, that is, they do not move, and hence their rotational loss will be 0. Since there is no rotational loss, efficiency will be high. That is one of the biggest advantage of the power electronics, that power electronics converter have high efficiency. Otherwise, one of the methods to convert AC into DC could be take 3-phase AC, apply it to an induction motor, which will give mechanical power, which will be coupled to a DC generator. Then it will give the DC output. But the thing is in that in both the machines we will have rotational losses, so efficiency of conversion will be less. Whereas if we use a rectifier to convert AC into DC, then the efficiency is very high. Due to this fact, the DC generators are obsolete nowadays, because if you want to generate electrical output as DC, then you can better convert AC directly into DC by means of power electronic converters. Now, if rotational losses are not there, heat reduces, due to which temperature reduces, due to which cooling requirement also reduces. If cooling requirement also reduces, due to which we make use of heat sink with the power electronic switches. That is, power electronic devices are always mounted on a heat sink which will dissipate the heat generated in the power electronic device. If it can dissipate the heat generated, then no need of additional cooling methods to cool down any device. Next is compact in size. As I told you, when we convert power from one form to another using machines, there will be two machines which will increase the size of system, whereas the size of power electronic converter can be as small as that it can be held in hand. Okay, so they are very compact in size. Next is that we can implement closed loop control. Now, why closed loop control is possible in power electronics? Because of the 3-terminal devices. Now, usually the switches that we use in power electronics have 3 terminals. 2 are used to carry current from one point to another, or 2 are called as power terminals, whereas one other terminal is called as control terminals, which controls the power conversion. So whatever control signal we were feeding in the power processing circuit, that will be fed to the control terminal. Whereas in case of electrical machines, we only have 2 terminals, which are actually the power terminal. So to control the speed or to control any parameter, you actually have to change the quantity at the power terminals. You do not have any additional control terminal. So that is also one of the advantage of the power electronics. Now, what are the disadvantages? The biggest disadvantage, always remember, in power electronics is harmonics. Now, what happens due to switching? That is, switching on and off, harmonics will be induced. Let me take an example. If we switch on and off a constant current, it will generate a square wave form. Now, this square wave always has harmonics because it is not sinusoidal. What is meant by harmonics is, Harmonics are the multiple of fundamental frequency when any function is expanded as a Fourier series. Now suppose this is I. If it is expanded as a Fourier series, sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t, then the terms which have any term that is except n is equal to 1 will be harmonic. The only desirable term is the fundamental, due to which harmonics are generated in the power electronic converters. So due to switching operation, most of the waveform in power electronic converters are non-sinusoidal but yet periodic, and hence they will have harmonic content. And if we were converting using the machines, then there would be no harmonics induced in the system. So that is the biggest disadvantage. But the question that arises in our mind is, now I know that there are harmonics. So the first question that comes to mind is, why remove harmonics? What is the disadvantage of harmonics? Now, the RMS value of current with harmonics will be under root I naught square plus half I1 square I2 square go on up to infinity. Now this is the amplitude of fundamental, amplitude of second harmonic. So this is my fundamental term, which is desirable. Rest of the terms are undesirable, which means that RMS value of the current increases due to harmonics in the system. If RMS current increases, then the losses, which are equal to I RMS square into R, they will also increase. So copper losses increase due to increase in RMS current of the system. Similarly, harmonics have a frequency of n omega naught or nf, due to which harmonic frequency is high, due to which core losses, which are proportional to frequency raised to the power n, in eddy current case it is square, in hysteresis case it is 1.6. So they will also increase. So core losses will also increase, which reduces the efficiency of the system. Also the impact lies on the power factor. Now suppose I consider a power electronic converter as 100% efficient. That means whatever is the input power will be same as the output power. Now input power will be Vs Is cos phi, where Vs is the supply RMS voltage, Is is the supply RMS current. P0, suppose it is DC output, V0 I0. So cos phi will be V0 I0 by Vs Is. Now as I told you, RMS current increases with increase in harmonics. So cos phi reduces. So it reduces the input power factor of the converter. If input power factor is reduced, that means the supply power consists of reactive power content, which is high, and it is undesirable. That is why power electronic converters require reactive power to operate, which in case of HVDC is supplied by means of compensators. Okay, in HVDC both terminals have power electronic converters, so they will be connected to the compensators. Otherwise, they will reduce the power factor of the supply side. Now, when we start the study of power electronics, first thing that we need to understand is Fourier series, because here a lot of waveforms will be encountered which will be non-sinusoidal, and to analyze the behavior of any converter we will need to extract the harmonics, for which we need to extract the Fourier series. Now Fourier series is defined for periodic functions, and here we are interested in trigonometric Fourier series, which expresses any function as a naught plus sigma n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Now here a naught is called as the DC or the average value. It is equal to 1 by t integral 0 to t, or let us say t, ft dt. Now if we wish to change the variables into omega naught t, we know that omega naught is 2 pi by t. So omega naught t is 2 pi. So if you multiply and divide by omega naught t, it will be 1 by 2 pi. Integration will be over an interval of 2 pi ft d omega naught t. This will be my a naught. That is the DC, or the average value of the Fourier series. Now the next coefficient, which is an is written as 2 by t integration over t ft cos n omega naught t dt. Again multiply and divide by 2 pi, sorry, by omega naught. So it will be 2 by 2 pi ft cos n omega naught t d omega naught t. Similarly, Bn will be 2 by t ft sin n omega naught t dt. If we convert it into omega naught t, it will be 2 by 2 pi integration over 2 pi ft sin n omega naught t d omega naught t. So these are the formulas which are used to derive the Fourier series coefficient. Now there are some properties of Fourier series that must be always kept in mind is, if the waveform is even function means ft is equal to f of minus t, then it implies Bn is 0. Only a0 and an are non-zero. Okay. And if it is an odd function, that is ft is equal to f of minus t, like this, then it is an odd function, then only Bn is non-zero, a0 and an both are 0. If it is half wave symmetric, that is minus ft, then only odd harmonics exist. Odd harmonics means n is equal to 1, 3, 5, 7, like that. Only these terms will exist in the Fourier series expansion. Now let us look at a few of the Fourier series that we will commonly encounter in our power electronics study. So whenever I will encounter these waveforms in future, I will directly use the results obtained in this lecture. So the first waveform is something like this, which remains at v from 0 to pi. So v0 is v from 0 to pi and minus v from pi to 2 pi. Now this is a periodically square waveform, and if we draw it before 0 like this, now how I am drawing it is, I am just repeating the pattern, negative, positive, positive, negative, negative, positive, like this. That means it is symmetrical in first and the third quadrant, hence only, sorry, it is actually odd function, so only sign terms will exist. So we just have to calculate Bn. Is it fine? Since it is odd. Now if you see, if you take an angle theta, the value at it is pi. If you take a value at pi plus theta, the value is minus v. So f of theta is equal to minus f of pi plus theta. Hence it is half wave symmetric, only odd harmonics will exist. Okay, so it will have sign terms with only odd harmonics. Now let me derive what is the Fourier series coefficient. So Bn will be 2 by 2 pi. I am integrating in terms of omega naught t. From 0 to pi it will be v into sin n omega naught t d omega naught t minus pi से 2 pi v Sin n omega naught t d omega naught t. Why minus? Because it is minus v. Now let me take this v common. It will become v by pi. Integration of sine will be minus cos n omega naught t by n from 0 to pi. Minus minus will be plus from pi to 2 pi. Now if we substitute the limits, so this will be, let me take out n common, v by n pi, then 1 minus, because cos of n0 is 1, plus minus cos n pi. Now cos 2n pi, that is cos 2 pi, 4 pi, 6 pi will be 1. Now if n is even, that is 2, 4, 6, then cos of n pi will be 1 and bn will be 0. If n is odd, cos n pi is minus 1. So bn is 4v by n pi. So the Fourier series can be expressed as since only odd harmonics exist, sin n omega naught t. So remember this Fourier series specifically as this waveform is actually output voltage of a single phase full bridge inverter. Okay, so there also we will use this Fourier series that we have derived just now. Next, let us move on to another waveform. Here this is actually the input current of single phase semi-converter. Semi-converter means semi-controlled rectifier. So this angle will be pi. So it is going from alpha to pi, then pi plus alpha to 2 pi. Now 2 pi is identical to 0. So this will be drawn like this. Now if you see, this is neither even nor odd because it is not symmetric in first and third quadrant and nor in first and second. So here we will have to calculate an as well as bn. But a0 I can directly say 0 because area will be 0. Positive area is equal to negative area. So we just have to calculate an and bn. So first let me calculate an. It will be 2 by 2 pi integral alpha to pi I cos n omega naught t d omega naught t plus minus I from pi plus alpha to 2 pi cos n omega naught t d omega naught t. So that will become I by pi. Integration of cos will be sin n omega naught t by n from alpha to pi minus sin n omega naught t by n from pi plus alpha to 2 pi. N can be taken as common, I by n pi. This will become sin n pi minus sin n alpha minus sin 2n pi plus sin n pi plus n alpha. Now if you see this waveform actually, if you take an angle theta after 0, the current is I. If you take pi plus theta, the current is minus I. Hence it is half wave symmetric. So odd harmonics only exist. Even will become 0. So if n is equal to even if we put here sine 2 pi, 4 pi, 6 pi will be 0. This will also be 0. Sine n alpha, then sine 2 pi plus something is sine theta. So this will get cancelled with the sine n alpha term. So an is 0. What if n is equal to odd? Then this term is always 0. But these two terms will become identical. So it will be minus 2i by n pi sine n alpha. Okay, because these terms will get added. Now let me calculate Bn. 2 by 2 pi, then alpha to pi I sine n omega naught t d omega naught t minus pi plus alpha to 2 pi I sine n omega naught t d omega naught t. So it will be I by pi, integration of sine is minus cos. This will be, okay, minus minus will become plus, so I can write okay. So n can be taken as common, I by n pi now for n is equal to odd, this cos n pi will be minus 1, cos 2 n pi will be plus 1. 1 plus minus 1 is 2. So 2 taken as common, this will be 1 minus cos n alpha. Because if n is odd, cos of pi plus theta is minus cos theta. So minus minus will become plus. This term and this term will get added. So 2 can be taken as common. Now since we have an as well as bn, let us combine it into a single Fourier series. So Fourier series will be n is equal to 1, 3, 5 up to infinity. An is minus 2i naught minus 2i by n pi. Then sine n alpha, then cos n omega naught t plus 2i naught by n pi 1 minus cos n alpha sine n omega naught t. Now to combine these two terms, first I can take 2i naught by n pi common. Then this sine theta can be written as 2 sine theta by 2 cos theta by 2. Similarly, 1 minus cos theta will become 2 cos square theta by 2. So what I will do is I will take rather 4i naught by pi common. Okay. Here it is coming sine theta by 2 cos theta by 2. Here cos square theta by 2. So let me take cos theta by 2 common. Then this term will be written as sine n omega naught t. 1 cos theta by 2 will remain. Minus this can be written as cos n omega naught t sine theta by 2 will remain. So this will be 4i by pi cos n alpha by 2 sine n omega naught t minus n alpha by 2. This will be the Fourier series for this waveform. Now let me show you a simpler method to derive this Fourier series. Since this is a very tedious method, I will define a new function. Let me say xt. This xt I am drawing something like this. First see this. Alpha by 2, pi minus alpha by 2, pi plus alpha by 2, then 2 pi minus alpha by 2, minus alpha by 2. So what I have done actually is I have shifted it by left by an angle alpha by 2. So what I can write is xt is equal to I t plus alpha by 2. We have shifted by an angle alpha by 2. Or we can say that it is equal to xt minus alpha by 2. That is, we have to shift xt by an angle alpha by 2 towards right to obtain it. So now if you see, this function is an odd function, so we just have to calculate bn. No need to calculate a0 and an. So this will reduce our task, and then we will replace omega naught t by omega naught t minus alpha by 2. So if you derive bn, it will come out to be, or let me say Fourier series directly, xt will come out to be sine n omega naught t. So to derive it, we will replace omega naught t by omega naught t minus alpha by 2. So what we will arrive at is like this, n omega naught t minus n alpha by 2. So this can hugely reduce our task. Moving on to the next waveform. This waveform actually represents input current of a single phase full wave rectifier or single phase full converter. Okay. Now let me apply the shifting principle to obtain the Fourier series to reduce the task. Now if you want to apply the shifting process, then we have to shift it in such a manner that we can arrive at a odd or a even signal. To arrive it at an odd signal, what I will do is I will define x something like this. Okay. So this will be pi, 2 pi. So actually xt will be equal to it plus alpha if we shift this by left to by an angle alpha, or we can say it is equal to xt minus alpha. That is, derive the Fourier series for xt and then shift it by an angle alpha. Now this is the waveform that we saw earlier also, the first sample. So the Fourier series of xt will be sigma n is equal to 135 4i by, since amplitude is replaced by I, sin n omega naught t. So the Fourier series of it would be sigma n is equal to 135 will remain same, 4i by n pi sin n omega naught t minus n alpha, because we will replace omega naught t by omega naught t minus alpha. So n will get multiplied. So this is the Fourier series which we can arrive at in single step instead of doing the tedious calculation. So let me summarize what we covered the basics. We first saw what is power electronics. Then we saw the applications. Then we saw advantages, disadvantages of the power electronics. Then we saw the Fourier series concept, and we saw some of the Fourier series that we will encounter in power electronics course throughout the syllabus. Okay, that is, we will encounter these waveforms in mostly the chapters of rectifiers and inverters. So in the next lecture, what we are gonna do is we will start with the Hi guys, in the last lecture we started with power electronics. We saw what is power electronics, what are its applications in respect to machines, power system, transportation, renewable energy sources. Then we saw the advantages, in which the biggest advantage with power electronics was that it has high efficiency of conversion. Then we saw disadvantages, in which the biggest disadvantage was harmonics introduced by the power electronic converters. Then we saw Fourier series, which is a prerequisite for the power electronics course, and we derived Fourier series for certain waveforms that are commonly encountered during this course. In this lecture, what we will do is we will be starting with the power semiconductor devices, which is our first unit for the power electronic course. Okay. Now, what are power semiconductor devices? Power semiconductor devices are the solid state electronic devices which are designed to operate at high values of voltages and currents. Okay, or which are designed to operate at power ratings. So these are solid state devices. Solid state electronic devices which operate at high rating. Some of the devices in this category are power diode, then thyristor family, similarly transistor family. Now, what is the speciality about the power semiconductor devices is they are designed that so that we can control their operation to change the form of power, that is from AC into DC or DC into AC. We can control their turn on and turn off so that we get a controlled output. So we wish to control their turn on and turn off. Now these devices are always designed to operate as switches. In power electronics, whenever we wish to change the voltage or any parameters of the power, then we need switches. So these are designed to operate as switches. Like in BJT, when you study, there are three regions of operation: cutoff, active and saturation. In active mode, it acts as a amplifier, and in the other two modes, cutoff and saturation, it acts as a switch. In saturation, it is in the on state. In cutoff, it is in the off state. Similarly, here all power electronic devices will be designed to operate as switches. Now, if we are designing any device to operate as a switch, then we must understand what is the ideal switch or what is the ideal characteristics of any switching device. Now, when we talk of ideal switch, these are the switches that we generally encounter in the circuits. Like in case of network, whenever we do transient analysis, we consider certain switches. Let us say a switch is closed at t is equal to 0, find the current. Such sort of switches are ideal switches. Now, what are the characteristics of ideal switch? When the switch is on, okay, when you close a switch, then its voltage is 0 and the current can have any value. When the switch is closed, it is called to be in the conduction state. In conduction state, voltage drop is 0 and current can have any value up from minus infinity up to infinity. Okay. Now, if we want to find the power of the switch, which will be equal to V on into I on, it will come out to be 0. This is called as your conduction loss. Okay. That means the loss of power in the switch when it is in the conduction state. So, for ideal switch, conduction loss is 0. Now, when the switch is open, in such a case, the switch must not carry any current. So, I off will be 0. And the voltage across the switch will be determined by the supply and the load, and it can have any value. Okay, so if we wish to determine P off, it will be V off into I off, that is 0. This is called as your blocking loss. Off state of the switch is also called as blocking state. So blocking loss must also be 0. Now when we study about switching of these sort of switches, we say that switch is turned on at t is equal to 0 or turned off at t is equal to t naught. That means the switching is instantaneous. Okay. So change of state is instantaneous. That means turn on time and turn off time both must be 0. So the switching time must be 0, due to which switching frequency is infinite. Now switching frequency being infinite means you can apply signal of any frequency at the terminals of this device. No matter what is the frequency of that signal, this device can be able to handle, because its limitation is the infinite frequency. The next property of ideal switch is it does not require any energy to turn on and turn off. That is, energy of turn on and turn off both is 0. Otherwise, what happens is, suppose we talk about BJT. In case of BJT, if it is acting as a switch, then also we need to apply base current to turn on and turn off. So we need to supply some power by means of biasing. But in case of ideal switch, we need not have any external source to supply the power to change the state of the switch. And the last property is it is stable under all operating condition. Okay, that means doesn't matter what is the value of voltage and current across the switch, its operation will be stable. Now let us understand how a practical or a real switch differs from this. Now the first assumption in ideal switch was there is zero on state voltage drop and the current can have any value. But in a practical switch, on state voltage drop is non-zero and the current can vary between certain minimum to a maximum value. Okay, like in case of diode. Now the thing is, on state voltage drop usually in case of analog electronics we take as 0.7. So on state voltage drop is non-zero and the current can vary from 0 to infinite. And as you keep on increasing the current at certain point, what will happen is the heat produced in the switch will be very high, due to which it can get damaged. So there will always be limit even on the maximum amount of current that can flow in the device. Okay, higher current implies higher power means higher heating. In the next assumption I said that when the ideal switch is opened, it carries zero current and it can have any amount of voltage. But consider a diode. When it is off, it carries a reverse saturation current. That means off state current is always non-zero and voltage can vary between certain minimum and the maximum value. Why? Because suppose if you keep on reducing the voltage and you go below the breakdown voltage, then the diode will break down and it will start conducting. Similarly, if you go above the knee voltage, then also it will start conducting. So we have a limitation on the minimum and the maximum voltage. The next assumption was it can turn on and turn off instantaneously. But here turn on and turn off will require certain time. So let me give you an example in reference to diode only. In diode, during the on state or during the forward bias state, the depletion width is small. Now depletion region, what does it indicate is the region in which there are no charge carriers. But in off state, depletion width is high, that is the region where there are no charge carriers is large. Now to increase the width of such a region, we need to remove the charge carriers. And if you need to remove the charge carriers, then you need certain time. That is how adding or removal of the charge carriers requires certain time, due to which on and off time are finite but non-zero. due to which switching time is non-zero and switching frequency is finite. Now suppose switching frequency comes out to be 100 kHz. So it defines the maximum frequency that can be applied across the device. You cannot go beyond the 100 kHz, otherwise the device will not be able to work properly because time will be lesser. So before it is even turned on, you will be starting to turn off the device. Then the operation will not be proper. Now the next assumption was that it does not require any energy, but here E on is not equal to 0. Similarly, E off is not equal to 0. Now, from where does it get this additional energy to turn on and turn off? It gets it in the form of drive circuit. With power electronic switches, we will apply drive circuit from where it will derive the power to turn on and turn off the device. And the last condition was stable under all operating condition, but here we will have certain thermal limit. That is, you cannot apply any amount of current, otherwise the losses will be high, heating will be high and device will melt down. To remove the heat from the device, we make use of the heat sink. Okay, that is why all power electronic devices are mounted on the heat sink so as to remove the heat generated in the device. Now let me draw the characteristic of ideal as well as practical switch. When we draw characteristics of switches, we consider two characteristics. One is the switch voltage, other is your switch current. Now suppose initially the switch is off. If the switch is off, then there will be certain voltage across the switch. When the switch is off, there will be certain voltage and the current will be 0. Like this. We are now talking about the ideal switch. As soon as you turn on the switch, the voltage will go to 0 and the current will become high. Like this. Then we again turn off, then voltage will again become high and current will again become 0. So this is the on state, this is the off state. So remember, in the off state the voltage is high, in the on state current is high. Now what about the practical switch? In practical switch, when it is in the off state, the current will be non-zero. Let me take another color. It will be non-zero and the voltage will be high. Now when you start it to turn on, then voltage will decrease gradually and current will also increase gradually. This time will be called as your turn on time. Okay. Now it will remain at a lower value but not 0. Current will remain at a higher value. Then again when you turn off, voltage will increase gradually. Similarly, current will also decrease gradually. So this is called as your turn off time. Okay. So for the practical switch, in the off state and on state, current and voltages are both non-zero, and during the switching it takes a finite amount of time. Similarly, when we talk about the stability condition, for an ideal switch it is stable under all operating condition. That means on the VI curve it can operate anywhere. Okay, any point is a stable operating point. But for a real switch, there will be limitations on the maximum and minimum voltage, similarly maximum and minimum current. Also there is a thermal limitation, that means Pmax, which will be equal to V into I, should be constant. We cannot exceed Pmax, that means Vi is constant, curve will be a hyperbola. So at the edges it behaves as a hyperbola. Okay. So the region inside this is called as SOA, which is the safe operating area. So for a practical switch, safe operating area is finite. For a ideal switch, safe operating area is infinite, which consists of all the 4 quadrants entirely lying in the SOA. Okay. So if all the 4 quadrants lie in the SOA, that means you can operate at any point on the curve and the operation will be stable. Now let us understand what are the various categories of switches. Okay. So the first category is based on type of control. How much control you have over the operation of a switch. The first type of switch is called as uncontrolled switch. Now in uncontrolled switch, we cannot control the switching on and switching off of the switch. That will depend on the supply. Means by application of any external signal, I cannot control whether the switch is in the on state or in the off state. That will entirely depend on the supply and the load. An example of this is diode. Now, when you apply a forward bias across the diode, that is VAK greater than 0, then it turns on. But there is no third terminal in the device which can be utilized to turn on and turn off the device. Similarly, when VAK is less than 0 and IA is not equal to 0, device is on, and if IA is equal to 0, device is off. Okay. So that is the characteristic of the diode. So it is a kind of uncontrolled switch. Which of the switches will be uncontrolled? Wherever you do not have a third terminal to apply the control signal to turn on and turn off the device will be called as uncontrolled switch. The next type of switch is called as semi-controlled. Now in semi-controlled type of switch, what happens is you can only control one state. That means either you can turn it on or you can turn it off, but not both. So one switching state is in my control, other switching state I cannot control. Those sort of switches are called as uncontrolled switch. What is an example? SCR. Here we can control the turn on by gate signal, but turn off will depend on supply, like the case of diode. So during turn off, it just like behaves as a diode, so turn off is uncontrolled. So those sort of switches are called as your semi-controlled switches. And the last category will be fully controlled. In fully controlled, we can control both the switching states of the switch, that is turn on as well as turn off. So here both switching states are controlled. Example, GTO, which is your gate turn off thyristor. Here the gate signal can be used to turn on as well as turn off the device. Then transistors. No matter what is the type of transistor, whether it is BJT, FET or IGBT, all are fully controlled type of switches. Okay. That means by application of control signal, you can turn on and turn off the device. So this is the first classification of switch based on whether or not you are able to control its operation. The next classification of the switch comes on the basis of what is the polarity of the blocking voltage and what is the direction of current flow through the device. Now first category in this comes as unipolar switch. Now unipolar switch means that the switch can block only one polarity of voltage. That means if you apply the other polarity or the other direction of the voltage, then it will turn on and will start conducting. So it can stay off only for a one polarity of voltage. Like in case of diode, if we apply negative voltage, then it can stay off but as soon as you apply positive voltage, it will turn on. So we show characteristics like this. How do we show this? That means up to this point, the current is 0 and the voltage is variable. Or you can show something like this, a solid line here. So it shows that for voltages up to from 0 up to VBR, current will remain 0. And since this point is shown as finite point, it means it is a real switch. For a practical switch, this entire negative x-axis will lie in the characteristic. Okay, because the breakdown voltage will be infinite. So that is the case of unipolar switch. Similarly, if it blocks positive voltage, then what will be the characteristic? Like this. So that is the case for a transistor. Usually the reverse blocking capability in the transistor is very low, so they can block forward voltage until you apply a gate signal or a control signal. When you apply the control signal, then this device will turn on. Similarly, next type of switch is your bipolar switch. In bipolar switch, what happens is it can block both polarity of voltage, positive as well as negative. An example of this is SCR. In negative, it behaves as a diode. In positive, it will block until you apply gate current. Until gate current is 0, it will stay off. So that is how it blocks the positive as well as negative voltage. Without the application of gate current, it won't turn off below this voltage. But as soon as you apply gate voltage either you apply a voltage higher than this or you apply gate current, it will turn on. Okay. So that is the characteristic of the bipolar switch. Similarly, based on direction of current, we classify as unidirectional switch, which means it carries current in only one direction. So characteristics will be like this, because when we talk about the on state of the switch, we consider the voltage drop as 0. So when it is conducting, it will lie on the y-axis so that voltage of the switch is 0. This is I, this is V. What is the example diode? It can only carry current from anode to cathode. SCR, anode to cathode. Transistors, they also carry current in one direction. So most of the devices are unidirectional. Similarly, the counterpart will be bidirectional. In bidirectional type of switch, it can carry current in both directions. An example of this will be triac. It is designed to have the bidirectional characteristics. So now let us see the characteristics of the power semiconductor devices based on this second classification. So first we take the case of a diode. Now based on the above classification, it is a unipolar and a unidirectional switch. So characteristics will have 2 points. This indicates the blocking state. This indicates the conduction state. So in ideal characteristics, we have to show both the blocking as well as conduction states. Now it is a uncontrolled type of switch, unipolar and unidirectional, and the safe operating area, that is the operating area of this switch, is this. This is your second quadrant. Okay. So that is how we determine the safe operating area between the current and the voltage limits. Now if we talk about the transistor, whether it will be BJT, which has a base, collector, emitter, or it is FET, drain, source, gate, or it is IGBT, gate, collector, emitter, all will have same characteristics. Emitter, all will have same characteristics, that is they will block one polarity of voltage and conduct current in only one direction. So it is a fully controlled type of switch, but it is unipolar and unidirectional, and the SOA will be first quadrant. Okay, so this is about the transistors. Next we see the SCR. How do we represent a SCR? Like this, three terminal device, anode, cathode and gate. It is a bipolar and a unidirectional switch. So characteristics will be like this. Okay, so it is a semi-control type of switch. It is bipolar and unidirectional, and the SOA will be first and the second quadrant. Next we talk about GTO. In GTO we have like this. So here it is a fully controlled switch, but the characteristics remain the same. The only difference between SCR and GTO is that GTO can be turned off with a negative gate pulse, but SCR cannot be turned off by gate signal. Okay. Next we consider triac. Triac behaves like two SCRs in anti-parallel. So this is termed as main terminal 1, main terminal 2 and gate. Why main terminal 1 and main terminal 2? Because it is a bidirectional device. It can carry current in both direction. So we cannot define anode and cathode, because if we define anode and cathode, then current always flows from anode to the cathode. So that is why triac will be named as main terminal 1 and main terminal 2. So it is a bidirectional as well as bipolar switch. Okay. And its SOA will be all the four quadrants, and it is a fully controlled type of switch. That is your triac. Next we consider the characteristics of body diode. Now what is a body diode? It is a parasitic diode in certain devices. Now basically what is a diode? A diode is nothing but PN junction. So in certain devices a PN junction is formed which will behave as a diode, and it carries current in opposite direction as compared to the device. So those devices are MOSFET and IGBT. Since it carries current in opposite direction, it is shown in anti-parallel. Like this is your gate, then drain, then source, and then diode will be anti-parallel. Since this MOSFET will carry current from drain to source, this diode will carry from source to drain. It will carry current in this direction and MOSFET in opposite. So it becomes a bidirectional switch. Similarly, in case of IGBT, there will be an inherent body diode like this: gate, collector, emitter. So due to which the characteristics change, and they are now something like this: unipolar and bidirectional. So why it is unipolar is because whenever you will apply a negative voltage, that is whenever VC is less than 0, or we can say VEC is greater than 0, then what will happen is this diode will turn on and it will start conduction. That is why it can block only one polarity of voltage. So remember, whenever diode is connected in anti-parallel to any device, the device behavior will be unipolar and bidirectional. Like if we connect a diode in anti-parallel to SCR, by default SCR is bipolar, but whenever a diode is connected, it will become unipolar and bidirectional. So that is the purpose of the anti-parallel diode. In these two devices, this anti-parallel diode is inbuilt, but in other devices, you have to connect an anti-parallel diode in external if you want to have a bidirectional behavior. Now let us see a problem. We are given a switch. We need to know which of the following devices can be used. Now when the switch is open, voltage can be positive as well as negative. This indicates a bipolar behavior. And since current is shown in only one direction, it is unidirectional. So we need to find which of these devices is bipolar and unidirectional. This is my SCR. It is by default bipolar and unidirectional. Here BJT is shown with an anti-parallel diode. So the first thing is this is external diode. Do not think that it is body diode. In case of BJT, there is no body diode. So whatever diode is shown is externally connected anti-parallel diode. Now, due to this external diode, the characteristic will be bidirectional and unipolar. As I told you, it cannot block negative voltage because when you apply negative voltage, this diode will turn on and carry current in opposite direction. So it is bidirectional. What about this? This BJT can carry current in this direction. Diode can carry current in this direction. So it is unidirectional. Opposite current is not allowed by either BJT or diode. What about the blocking capability? When you apply positive voltage, it will be blocked by BJT, so it will stay off. And since both are connected in series, for the switch to turn on, both must be on. Whenever either one switch is off, the entire switch will be off. So it will block positive voltage. What about negative? This BJT won't be able to block negative voltage, but this diode will not conduct for negative voltage. That is, it will not conduct when the polarity is like this. So it will block negative voltage. Okay, so it is bipolar. For positive voltage, BJT will block. For negative voltage, diode will block. And for the device to turn on, both must be on. So whenever either one is off, device is off. So answer will be these two. Now suppose we wanted to make this switch bidirectional. How to do that? Remember, whenever you want to make any switch bidirectional, then you connect two such switches in anti-parallel. How to do that? You connect something like this. If you connect two switches like this, this is my control terminal C and power terminal A and B, then it becomes a bidirectional switch because one device will carry current in one direction, other in opposite direction. So to get a bidirectional behavior without changing the unipolar or bipolar, we connect two identical switches in anti-parallel. But if you want to have bidirectional and unipolar behavior, connect an anti-parallel diode. So let me summarize what we covered in this lecture. We first saw what is meant by power semiconductor devices, and I told you they operate as switches and not in the active mode. Then we saw what is meant by ideal switch and a real switch. We compared the characteristic of both. Then we classified the switches based on their control characteristics like uncontrolled, semi-controlled and fully controlled. Then we classified the switches based on unipolar, bipolar, unidirectional, bidirectional. And then we saw the characteristics of the power semiconductor devices based on their polarity and the direction of the current flow. So that is what we have covered in this lecture. In the next lecture, we will study about the losses in the switch. Hi guys, in the last lecture we started our study of power semiconductor devices. There I told you about power semiconductor devices being operating in the switching mode. They never operate in the active region or the linear region. Now, why they operate in the switching mode? Because to realize power electronic converters, we need switches. Then we saw what are the ideal characteristics of a switch and what are the practical characteristics or real characteristics of a switch. Now, based on real characteristics of the switches, we saw classification of the switches, in which first classification was based on control offered by the switch, that is uncontrolled, semi-controlled and the fully controlled switch. And then we saw second classification based on the polarity of voltage that is blocked by the switch and the direction of current that is conducted by the switch. So we saw unipolar, bipolar switch, unidirectional and bidirectional switch. Then we saw characteristics of the power semiconductor devices based on their unipolar and bipolar, unidirectional and bidirectional behavior. And we saw whenever we are given a design objective to design a bipolar or unidirectional switch, we can construct such a switch by the combination of power semiconductor devices. Now in this lecture we will study about the losses that occur in a power semiconductor device or in a switch. So the first loss that is encountered is the conduction loss. Conduction loss is the loss in on state. Now, how to determine the loss in the on state is average power loss. If we wish to determine, it will be 1 by time period of switching, then the on time period of the switch, V on I on into dt. Okay, that is, first we will calculate the energy during the on state and then we will divide it by the total switching period to determine the average power loss or average conduction loss. Now whenever we are considering the switches, either we must be given V on and I on. Then the first thing that you will do is, suppose we have two waveforms, one corresponding to V on and other I on. Then first you will take the product to determine P on, that is V on into I on, and then you can determine the average of such a curve. That means by two constituent curves V on and I on, I have generated a new curve that corresponds to on state power loss, and then we calculate the average of such a curve from the curve itself. Or other way to determine the average power loss is by modeling the switch. Now usually in the on state, switches are modeled as different electrical circuits. Like, first if we take a diode, it is modeled as constant voltage drop. Now as we see in the analog electronics also, diode is modeled as a constant voltage drop of 0.7 volt, or we can say the knee voltage. That means V on is constant. So from the power, V on can be taken outside 1 by T integral I on dt. Okay. Now the term inside the braces represents average current. So it will be V on into I average. So if we determine the average of the waveform or the current waveform, then we can determine the power loss in the switch. Now some switches like MOSFET are modeled as a constant resistance RD. Now if the resistance is constant, current is I on, then V on will be I on into RD. So what will be the on state power loss? 1 by T integral V on into I on will be I on square RD dt. Now if you take RD common, it is constant. I on square into dt. Now average of the square is the square of RMS. I on RMS square into RD. Okay, or we can say V on square RMS by RD. So this way, whenever it is modeled as a resistance, then you will use the RMS value of the current. So remember, when it is modeled as a voltage source, use the average value of current. When it is modeled as a resistance, then use the RMS value of current. But what if it is modeled as a resistance as well as voltage? Then what we will do is, on state power loss will be V into I average plus RMS square into RD or R. Okay. So that is how you will determine the on-state power loss. We will add both the terms, that is the average current term and the RMS square term. So this is your conduction loss, and that is how you determine based on different models of a switch. So let us look at few problems based on this. In the first problem, it is saying the current flowing through and voltage of the power electronic switch is shown in the figure. This is my V switch, this is my current in the switch. First we need to determine average and RMS value of the switch current. Now I average is nothing but 1 by T integral I switch dt. Now in this region we can model the switch as a straight line, current as a straight line. So I switch will be how much? The slope is 10 divided by Ts upon 2 into T, since this line passes through origin. So it will be 1 by T 0 to T, that is 20 by Ts T dt. The square of T integral will be T square by 2. So 20 by Ts square, this will also be Ts, will be T square by 2, that is 0 up to Ts. Now I will put the limits, it will be Ts square by 2, that is 10 ampere. So that the average current will be 10 ampere. Okay. This limit will be Ts by 2 because it is 0 from Ts by 2 up to Ts. So this will be 10 by 4, which is equal to 2.5 ampere. Or the other way to calculate the average current is just take the area. What will be the area of triangle? Half into 10 into Ts by 2 over total time period, that is Ts. So it will be 2.5 ampere. This is your average current. Now we need to calculate the RMS current. To calculate RMS current, we will divide by Ts integral of I square dt. Now it will be 1 by Ts, I square will be 400 by Ts square T square dt from 0 up to Ts by 2. Okay, which means it will be 400 by Ts cube, and integration of T square will be T cube by 3, 0 up to Ts by 2. This whole will be under root. Now IRMS will be under root 400 by Ts cube into Ts cube by 24. So it will come out to be 100 by 6. that is 10 by root 6 ampere. In the next part, it is asking about power loss in the switch. So as I told you, one of the best method to determine power loss is multiply the voltage and current waveforms to obtain the power waveform. In this region, voltage is 1. So the power will be same as that of current. And here the current is 0, so power will be 0. So what will be the power waveform? Same as that of current. So this will be 10 watt. Now if we wish to determine the average, we will just take the area, that is half into 10 into Ts by 2 divided by the duration. So it will be 2.5 watt. Or otherwise, if we apply direct method, then if you see here, the voltage in the on state is constant. So switch is modeled as a constant voltage drop. So average power will be V on into I average. So V on is 1, I average was 2.5. So this is 2.5 watt. Okay, because in this region there will be no power loss. Though the voltage is there, current is 0. And anyways, this loss will be counted as the blocking loss. When current is 0, switch is in the blocking state and the losses will be blocking loss. In our next problem, it is saying a MOSFET rated for 15 ampere carries a periodic current as shown in the figure. We have been given the on-state resistance of the MOSFET. We need to find average on-state power loss. Now, the MOSFET is modeled as a resistance. So here, power loss will be IRMS square into RD. Now here, that means we need to calculate RMS. So IRMS will be under root 1 by 2 pi 0 to pi 10 square, that is 100 dt. Then d omega t. Then it will become 10. We are taking 100 common. 1 by 2 pi into pi. That is 10 by root 2. So power loss will be IRMS square, that is 100 by 2 into 0.15. That is equal to 7.5 watt. So that will be the power loss in the switch. So remember, power loss expression depends on the modeling of the switch. It can use average current as well as it can use RMS current depending on how you model it. The next type of loss in the switch is called as switching power loss. Now what is meant by switching power loss? In case of real switch, what we saw? There was finite on and the turn on and the turn off time. That means it takes a finite amount of time to change its state. In that duration, both the current as well as the voltage are non-zero. Hence, the power of switch is non-zero, due to which losses are there in the switch called as switching power loss. So that means the losses in the switch whenever the switch changes its state from on to off or from off to on is called as switching power loss. Now how we model the characteristics of the switch? Now first let us take in the off state. Switch is in the off state, then it starts turning on, then it turns off. So this is my I switch. Similarly, V switch will be how? Switch characteristics will be like this. When the switch is off, voltage is high, then voltage drops, then voltage is 0, then voltage again increases like this. So this is the turn on procedure in which voltage reduces, current increases. This is my turn off when the voltage increases and current reduces. Now suppose this is V, this is I. So now to determine the switching power loss, we write the equations of V as well as I during the turn on and the turn off time. So first let me consider the turn on. Now during the turn on, what to do is, you consider t is equal to 0 here and t is equal to t on here. Now what will be the equation of current? Current will be I by t on, that is the slope, into t. Voltage will be V 1 minus t by t on, because voltage at t on is 0 and voltage at 0 is V. Now if we calculate Vi, it will be Vi by t on, t minus t square by t on. So what will be the energy in the on transition? It will be 0 to t on Vi dt. So if we integrate it, it will become Vi by t on. Integration of t will be t square by 2. So t on square by 2. T cube by 3. T on cube by 3 t on. So it will be Vi by t on into t on square by 6. So it is equal to Vi by 6 into t on. Now if we consider the turn off transition, so what to do is, in turn off, again take the same procedure. Consider here t is equal to 0 and this as t is equal to t off. Why I am doing so? Because it simplifies the calculation. Now the equation of current will be, now it is decreasing, I 1 minus t by t off, and voltage is increasing, it will be V into t by t off. So power will be Vi by t off, t minus t square by t off. So it is a similar expression, just t on has been replaced by t off. So that is why energy in off will be Vi by 6 into t off. So total energy or the switching energy loss is Vi by 6 t on plus t off. So that is how you determine the switching power loss. You have to write the equations for voltage and current and then multiply both to integrate them and determine the energy loss. And if it asks about the power loss, it will be F into energy loss. Or we can say energy loss by time, which will give me the F into energy loss. So that is how to determine the switching power loss. And remember, switching power losses are kind of most dominant losses in the power semiconductor switch. They are more than the conduction power loss. So let us see a problem based on this. It is saying the figure shows the voltage across a power semiconductor device. So this is the voltage waveform and the current through a device during the switching transition. Is the transition a turn on or a turn off transition? Now, first of all, if you see the transition, here the voltage is reducing, current is increasing. Now when the switch is on, current is high, voltage is low. So this is turn on transition. Okay, because current is increasing to a higher value, voltage is falling to a low value. So that is why it is a turn on transition. Then it is asking about the energy loss. So for calculating energy loss, we have to consider two regions, 0 to T1 and T1 to T2. So from 0 to T1, voltage is equal to constant, current is equal to I is equal to I into T by T1. That is the equation of a straight line passing through origin. So power will be Vi T by T1. So that means the energy will be integral 0 to T1 Vi T by T1 dt. That is Vi by T1, integral of T will be T square by 2. So that is Vi by 2 into T1. Now, if we want to calculate the energy loss in the off transition, we will consider this as T is equal to 0, T is equal to T2. Why we are considering T is equal to 0 here? Because the equations that we form for voltage and current are much more simplified if we consider origin as one of the points. And anyways, power loss does not depend on the choice of origin. Then voltage will be given as V 1 minus T by T2 and current is constant in that period. So power will be VI, that is VI 1 minus T by T2. So energy in T2 will be 0 to T2 VI 1 minus T by T2 dt. So that is VI, integral of 1 will be T minus T square by 2 T2 0 to T2, that is VI T2 by 2. So energy will be VI by 2 T1 plus T2, that is energy during both the periods. So this is the energy lost in the switching of the device, and if we multiply it by frequency, we will get the energy loss or the power loss in the switching. So that is why switching power loss will be proportional to frequency. Hence, we always have a trade-off between the losses in the switch and the frequency of the switch. Higher the frequency of operation, higher will be the switching power loss. So we will have to make a trade-off. The next we come to classification of devices. Now devices are basically classified into two categories. One is your majority carrier device. Other is your minority carrier device. Now first of all, what is meant by term majority carrier and minority carrier? In majority carrier, what happens is, whenever we talk about the semiconductors, there are two types, p-type and n-type. In p-type, always there is an excess of holes. In n-type, there is an excess of electrons. So electrons in the n-type region will be called as majority carriers because they are higher in number. Whereas electrons in the p-type region are called as minority carrier because they are lower in number. Similarly, holes in p-type region are majority carrier, in n-type region are minority carrier. Now whenever there is a p-n junction, what happens here? Holes are majority carrier, but when they enter the n region, they will become minority carriers. Such sort of devices are called as minority carrier device. So remember, which are the minority carrier device? Wherever the current flows through a p-n junction. Because in one region, one charge carrier behaves as a majority carrier, in another it will be a minority carrier. Then what are the majority carrier devices? In which there is no p-n junction in the path of current. Like in the case of MOSFET, there are drain and the source region. In between there is a n channel. So current flows between two n plus region through a n channel. Hence it does not encounter any p-type region. So this is a majority carrier type of device. So which devices classify as majority carrier? The MOSFET or a Schottky diode, because in a Schottky diode there is no concept of n junction, it is a metal semiconductor junction. So whatever charge carriers are there, they will be the majority carriers. Which are minority carrier device? Power diode and BJT, because in BJT also we have PNP and NPN configuration. So there always a PN junction is formed. Now what is the difference between these two categories of devices? Now in majority carrier device, we have high breakdown voltage under light doping. Light doping means when the doping density is low. And in minority carrier device, we have high breakdown voltage always. Doesn't matter whether the doping is high or low, it will always have a high breakdown voltage. Here we have high on-state resistance, due to which conduction losses are high. Here on-state resistance decreases due to conductivity modulation. I will tell you about conductivity modulation in the coming lectures. R-on reduces, due to which on-state losses are less. In case of majority carrier device, switching times are less. Why switching times are less actually? As I told you, whenever you want to turn off a device, you have to remove the charge carriers. Now, let us take an example of diode. In diode, the depletion width is less in the on state and depletion width is high in the off state. So if you wish to increase the depletion width to turn off the device, then you have to remove the charge carriers near to the junction, which requires certain time. So these are called as stored charge carriers. But in a majority carrier device, there are no such stored charge carriers that you have to remove. So turn off time is reduced and hence switching time is less. Here switching time is high. So here switching frequency will be high, 1 upon T switching. Here switching frequency will be low. Okay. So this has a lower speed and a majority carrier device operates at a high speed. It has a low voltage rating. Why low voltage rating? Because already the losses are high. To reduce the losses, you will have to reduce the rating. Here we have high voltage rating. Okay, because the losses are less and hence we can operate at higher voltage. Example of majority carrier, MOSFET and the Schottky diode, and minority carrier is BJT and the diode. Okay. Now one of the challenges in the power semiconductor device design is to have a high breakdown voltage. In power semiconductor devices, how we achieve it? We achieve it by introduction of a drift region. Drift region is actually a lightly doped region. Now what happens is, if you consider electric field as constant, then breakdown voltage is directly proportional to depletion width. Okay. Now consider a PN junction. Now by charge continuity, in P region we will have acceptor ions and here we will have donor ions. By charge continuity we can write NaXP is equal to Nd into Xn. That is number of charge carriers into depletion width in P region, that is Xp. That means both the layers are depleted equally, because whenever depletion occurs, then what happens? An electron and a hole recombine. So the number of electrons recombining will be same as number of holes recombining. Hence the total charge in the depletion region will be same on both the sides. In such a case, this is called as your continuity equation. Now suppose Nd is reduced, that is the light doping, then Xn increases. Due to this increase in Xn, what happens? Depletion width increases, Xp plus Xn increases. Now if depletion width increases, breakdown voltage increases. That is why introduction of a lightly doped region increases the breakdown voltage of the device. Okay, because electric field is constant, the higher the depletion width, higher will be the breakdown voltage. Okay, but conductivity is directly proportional to number of charge carriers. If you introduce the lightly doped region, number of charge carriers reduce, conductivity reduces. So on-state resistance increases. So this lightly doped region has two impacts. It increases the on-state resistance, but it also increases the breakdown voltage. Now increase in the on-state resistance is not an issue for a minority carrier device, because there, due to conductivity modulation, on-state resistance reduces. But in majority carrier device, it is an issue, because the conduction losses will be higher, as there is no concept of conductivity modulation. Okay, that means this lightly doped region is preferable in the minority carrier device as compared to the majority carrier device. Now as we saw, majority carrier device have high frequency but low power, and minority carrier device have high power and low frequency. So depending upon the frequency and the power rating, we will choose either a minority carrier or a majority carrier device. Majority carrier will be chosen for low power high frequency application and minority carriers for low frequency high power application. So that is one of the criteria to choose a minority carrier or a majority carrier device. Other criteria is called as temperature coefficient. Now what is temperature coefficient? It indicates the change in resistance of the device with change in temperature. Now there are two types of temperature coefficient. It can be positive as well as negative. Positive temperature coefficient is written as PTC, positive temperature coefficient, negative as NTC, that is negative temperature coefficient. Now positive temperature coefficient indicates that resistance increases as temperature increases. Negative indicates resistance reduces as temperature increases. Now whenever we are talking about parallel operation of switches, now why do we connect devices in parallel to increase the current rating? Because in parallel current will be divided, so we can apply more current. Now if their devices are negative temperature coefficient, then as current increases, the heat will increase, due to which temperature will increase, due to which resistance will reduce, due to which current will still increase. Due to this, there is this cycle in which current goes on increasing. This is called as thermal runaway, or it is also called as second breakdown. So minority carrier devices have usually negative temperature coefficient and they have a problem of second breakdown or the thermal runaway, which is undesirable. Hence, these devices are not recommended for parallel operation. That is why BJT is not recommended for parallel operation, but MOSFET can be operated in parallel as it is a majority carrier device and hence has a positive temperature coefficient. So remember this concept. BJT have a second breakdown problem, that is they will get damaged due to this thermal runaway. It is also called as second breakdown. So let me summarize what we covered in this lecture. We first saw conduction losses. There I told you if V on is constant, conduction loss is V on into I average. If RD is taken as constant, conduction loss is IRMS square into RD. If both are taken, it will be V on into I average plus IRMS square into RD. Then we saw switching power loss. It was 1 by T V switch I switch dt. So we saw it is proportional to frequency. Then we saw majority and minority carrier device. We saw majority carrier have high frequency low power and minority carrier have low frequency high power. Also majority have positive temperature coefficient and can be used for parallel operation. Minority have that negative temperature coefficient and cannot be used in parallel operation. In the next lecture, we will be starting with the power semiconductor devices one by one. So we will be starting first of all with the power diode. Hi guys, in the last lecture we saw the characteristics of the power switches. There we saw different type of losses. First loss that we saw was the conduction loss. This was the loss that occurred when the switch was in the on state or in the conduction state. And we considered different cases. When V on was constant, this loss was coming out to be V on into I average. Then when RD or the resistance is constant, then this loss was IRMS square into RD. When we are given V on as well as RD, then it is V on into I average plus I RMS square into RD. Then we saw the next category of loss was switching power loss. This was dependent on the turn on and the turn off time of the device. So we derived a general case in which it came out to be Vi by 6 T on plus T off. This was the switching energy. Switching power loss will be equal to frequency into switching energy. So we saw there is always a trade-off between the switching frequency and the power loss. Next we saw majority and minority carrier devices. We saw majority carrier devices are used at low power high frequency and minority at low frequency high power. Also majority have positive temperature coefficient whereas minority have negative temperature coefficient, so they cannot be used for parallel operation. Minority example was BJT and diode. Majority example was MOSFET and Schottky diode. In this lecture, we will begin our study of power semiconductor devices based on each and every device. So the first device that we will consider will be power diode. Now, power diode is basically a higher power counterpart of the signal diode. In signal diode, what was the structure? It is simply a PN junction. But here we need to modify the design in order to increase the ratings of this diode. So that means power diodes are more complex in structure as well as in operation as compared to signal diode. Why they are more complicated? Because we make modifications to the design in order to increase the rating. Now the modification that we do is we introduce a N minus region between the P and N region. This is called as your drift region. Okay. So it is introduced in order to increase the breakdown voltage of the device. So that is the modification that we do in case of power diodes. Now since power diodes will have higher current rating, that means losses will also be high. Now since losses are high, the heat generated will also be high, due to which temperature rise will also be high. Hence we require heat sink in case of power diodes as compared to signal diode. That is why power diodes are always mounted on heat sinks in order to dissipate the heat generated in the junction or heat generated in the device. So let us see in what cases power diode will be on and in where it will be off. So in case of forward bias, what is meant by forward bias is when we apply a positive potential to the anode or the P region and negative potential to the cathode or the N region. Then what happens? Due to positive negative terminals, an electric field is created in this direction from P to N. Now due to this electric field, the excess holes will feel the force in the direction of field. So holes will flow like this. Resuming the lecture. So when holes will flow from P region to the N minus drift layer, they will become minority carriers. Now N minus means it is lightly doped, due to which concentration of charge carriers is less. Okay. Since concentration of charge carriers is less, which charge carriers will be present here? Electrons. So concentration of electrons is very less, due to which majority of the holes entering this region will not be able to combine with the electron. Now suppose 100 holes are coming, but here only 10 electrons are present. So only 10 will be recombining. Rest of the 90 holes will reach this N plus layer or the N layer. N plus means heavily doped. Now what happens when these holes will enter the or will reach the N plus layer, they will attract the electrons from the N plus layer, due to which now electrons will also be entering the drift region. Holes are also entering the drift region. Now these holes and electrons will recombine inside the drift region. Okay, because if you understand, electric field is from left to right, electrons will be deviated in the opposite direction. So electrons will travel from N region to the drift region. Similarly, holes will travel from P region to the drift region. Now what happens is, conductivity in case of semiconductors is given as E n mu n plus p mu p, where n is the number of electrons, p is the number of holes, mu n is the mobility of electron, mu p is the mobility of hole. E is the charge of an electron. Now as the number of charge carriers increases, conductivity increases. Either holes or electrons increase. Similarly, as holes or electrons decrease, conductivity reduces. So what happens is, when electrons start entering the drift region, so concentration of electrons in the drift region starts to increase. As the concentration of electrons or the charge carriers increases in the drift region, its conductivity increases. This is known as conductivity modulation. So let me explain you what happens once again. Whenever we forward bias a diode, electric field is created from the P region towards the N region. Holes are deviated in the direction of electric field, whereas electrons are deviated in opposite direction, due to which holes will travel from P region towards the drift region. Similarly, electrons will travel from the N region towards the drift region. And in the drift layer, both holes and electrons will recombine. Now since electrons enter the drift layer, the density of electrons is increasing inside the drift layer, due to which conductivity of the drift layer increases and its resistance decreases. This is known as conductivity modulation. That is why in case of minority carrier device, on-state resistance is less. It is because of the phenomena called as conductivity modulation. Next, let us understand what happens in the reverse bias. In reverse bias, we apply a negative potential to the anode and positive potential to the cathode, due to which electric field is created in opposite direction. Now if electric field is created in opposite direction, then holes will not be able to enter the drift layer, neither the electrons will be able to enter the N from the N region towards the drift layer. So current is almost negligible because a very less number of holes or electrons are able to move. How come electrons and holes are able to move instead in spite of the electric field being in opposite direction? The holes and electrons that moves are usually minority carriers. What happens is, in P region also there will be some sort of electrons, and those electrons will be deviated in a direction opposite to the electric field. That is, those electrons will travel towards the right. Now these electrons are the minority charge carriers that are present inside the P region. They will travel towards the N region and constitute the current, which is also known as reverse saturation current. Okay. Now whenever a diode is reverse biased, it has a depletion layer formed. Why? Because what is the basic structure of a diode? Let me explain that. In diode, this is a P region, this is a N region. Now in P region there are holes, and holes are basically negative ions with a vacancy. Okay, negative ion has a negative charge and hole is considered as a positive charge. So overall this atom is neutral. Similarly, N region has positive ions with electron. Now when these both combine, then what happens? Negative ions will donate a hole, or they will absorb an electron from the positive ion. So this will be like this. So in this layer there are no electrons or holes. This is called as depletion layer. So if you apply a reverse bias, then what happens is, electrons and holes will recombine and the width of this depletion layer increases. In reverse bias, depletion width increases. Okay. Now, as we consider potential difference as electric field into distance, if electric field is assumed to be constant, then we can say that almost reverse voltage is directly proportional to depletion width. Actually, it is a under root relation which I am not showing here. Just for qualitative analysis, I am saying that as depletion width increases, the voltage will increase. That is why reverse breakdown voltage is high in case of power diode. Why? Because depletion width increases. How depletion width increases? It is due to this lightly doped region, because lesser is the doping, higher is the depletion width. And that I explained you even in the last lecture. It is by the means of continuity equation, because number of charge carriers in the p region into distance of p region, then charge carrier density in n region into width of the n region should be same, because if 10 electrons are recombining, they will be recombining with the 10 number of holes. Okay, so that is why number of uh, holes depleted will be same as number of electrons depleted. Hence, Na into Xp will be equal to Nd into Xn. If you reduce the doping density, then the depletion width increases. Is it fine? Xn is the depletion width extended into the N region, and Xp is the depletion width in the P region. So due to light doping, depletion area mostly extends into the N minus layer or the drift layer, which increases the effective depletion width and hence increases the breakdown voltage. So now, if we see the characteristics of the diode, first of all, let me explain the characteristics of signal diode. Signal diode has exponential current in the forward bias region, and the current is reverse saturation in the reverse region. But as soon as the diode encounters the breakdown voltage, current increases in the reverse direction. This is by the phenomena of avalanche breakdown. What is avalanche breakdown? If we apply a high reverse bias, then what happens is charge carriers begin to flow, and these will strike other atoms, which will cause more charge carriers to be produced, due to which charge carriers will increase exponentially and current will grow in the reverse direction. So what it means essentially is, due to introduction of charge carriers in the reverse direction, they will create more charge carriers and thus create a flood of charge carriers called as avalanche breakdown. But in power diode, the essential difference with the signal diode is its forward voltage drop is higher. Okay, that means forward voltage drop is higher as compared to a signal diode. In case of signal diode or analog diode, the voltage drop is taken as 0.7 volt. But here in case of power diode, it is 0.8 to 1.0 volt. And now if we see the reverse characteristic, reverse breakdown is voltage is higher for the case of power diode. Just now I told you why reverse breakdown voltage is high. It is due to introduction of the drift region between the P and the N region. Whenever the diode voltage is higher than this cut-in voltage, the diode begins to conduct. Before that, the diode current is negligibly small, and we can say that diode current is almost zero. This voltage is also called as knee voltage or the cut-in voltage. Is it fine? So that is how the characteristics of the diode will look like. Now let us understand what is the significance of drift region. Now drift region causes increase in the depletion width in the N region, due to which breakdown voltage increases. So that is the primary purpose of introducing a drift layer between the P and N region, to increase the reverse breakdown voltage. Okay, that means higher is the thickness of the drift region, more is the reverse breakdown voltage. So that is why that is why the drift region has a high thickness. If you see in the diagram here as well, the thickness of the drift region is much higher as compared to the P plus and the N plus region, because What we want is this depletion width that is being formed should not extend into the n plus layer. Okay, it should stay within the n minus region. It should not punch through. Is it fine? This depletion layer should not punch through to the n plus layer, and for that thickness must also be high, so that depletion width is always less than the thickness. That is why I am telling, as the thickness of the drift layer increases, your breakdown voltage increases. Okay, so basically thickness decides the reverse blocking capability of the diode. Reverse blocking capability means the maximum reverse voltage which the diode can block. That is actually the reverse breakdown voltage. But since this drift layer has less number of charge carriers, conductivity is less, due to which Ron is high. But in case of minority carrier devices, due to conductivity modulation which I just told you about, on state resistance reduces. Okay, it is due to the phenomena of conductivity modulation. And due to high resistance, what happens? There is large power loss, due to which device gets overheated. But in minority carrier, it is not a problem because of conductivity modulation. So remember, whenever we will introduce a lightly doped region in a majority carrier device, it will cause higher losses as compared to minority carrier device, because there is no phenomenon of conductivity modulation in the majority carrier devices. Now let us understand the parameters of a power diode. Now the parameters of a power diode are divided into two broad categories. One is the DC parameter, other is the AC parameter. So in the DC parameter, first is the forward voltage. Now what is the forward voltage? It is the voltage drop across the diode, that is VAK, anode to cathode voltage, when diode is in the conduction state. Okay, that is called as your forward voltage. Next is your breakdown voltage. Now breakdown voltage is the negative voltage which, if applied across the diode will break down and start conducting in the reverse direction. That is, IA will become less than 0. So we must always operate the diode below the breakdown voltage, or the diode must be chosen in such a way that the maximum negative voltage across the diode is less than breakdown. The maximum negative voltage across the diode is also called as PIV, which is the peak inverse voltage. It must always be less than reverse breakdown voltage. Next is your reverse current. Now what is the reverse current? It is actually the reverse saturation current, that is the current that is flowing in the diode when it is reverse biased, but for a voltage less than breakdown voltage, because above breakdown voltage current will increase exponentially. So this is defined below the breakdown voltage. But the area of interest is the AC diode parameters. That is, whenever we will apply a alternating voltage or current, then what happens? The diode will be forward bias for half cycle and reverse bias for another half cycle. That is, for half cycle it will be on, and for other half cycle it will be off. So that means it has to switch between the on and off state continuously. What happens if it switches between on and off state continuously? It has to regain its blocking capability when it goes from the on state to the off state, because in the off state it has to block the reverse voltage. That means to block the reverse voltage, depletion width must be high. That is why going from the on state to off state, one requirement is the increase in the depletion width. It is also called as regaining the blocking capability of the diode. So diode must always regain the blocking capability in order to be off during the reverse bias period. So in the AC diode parameter, first term we define as forward recovery. Forward recovery is, it is the recovery of the diode of its conduction characteristics. That is, when it is going from off state to on state, it must be able to regain its conduction capability. That is, the depletion width must reduce so that diode again can start conduction. It is just the opposite of the turn off procedure. So we define a forward recovery time. That is the time taken by diode to regain its forward conduction capability. Okay, that means it is the time taken by the diode after forward biasing to start conduction. That is, it is the delay between the point of forward biasing the diode and the time at which the diode begins to conduct the current. Because some time will go in reducing the depletion width, after that only the current will start increasing. Similarly, we define the reverse recovery time. It is the time after the anode current has been reduced to zero and the diode to recover its reverse blocking capability. After the current goes to zero, ideally the diode must turn off. But after the current goes to zero, it has to remove the stored charge carriers near the depletion region so that depletion width increases, and the time taken to do that is called as reverse recovery time. Again, I am repeating, whenever you are turning off a diode, then you are essentially reducing the current. Now, when the current reduces to zero, the diode must turn off, but it does not happen. What happens is, diode starts conducting in the reverse direction in order to remove the stored charge carriers during the forward biased condition, and that is called as the reverse recovery. If you see here, the diode current was reducing. This is the anode current. Now here at this point the diode must have stopped conduction, but it conducts in the reverse direction in order to remove the stored charge carriers in the depletion layer. What is meant by stored charge carriers? See, let us say this is my depletion width. Now beyond this, this will be p region, that is negative ions with holes. Here there will be n region, positive ions with electrons. Now if you wish to increase the depletion width, then these ions must also form a part of depletion layer. For that you have to remove these holes from the p region and these electrons from the n region. These are called as stored charges. So to remove the stored charges near the depletion layer, it takes some time or it conducts in the reverse direction. Because to remove the holes, holes must flow in this direction and electrons in this. That is why it is conducting in the reverse direction. That is called as reverse recovery. And if you see in the forward recovery, initially the current was 0. Now current gradually increases. Okay. As the current gradually increases, the voltage across the diode experiences a spike. How it experiences a spike actually? Suppose we take a RL circuit. Then what happens is, as the diode current is increasing, the diode hasn't fully turned on. So the voltage of the diode is, the voltage of the resistance will be almost 0. Okay, because the current is almost 0. Until the diode has turned on, the current is almost 0, so the voltage is also 0. But as the current increases, this voltage will be positive. There will be a voltage L di by dt, because though the current may be 0, di by dt is non-zero. Now due to this, the voltage difference appears across the diode, which will experience a spike until this resistance handles the voltage. Because when resistance will also have a voltage, then the diode voltage will reduce. Because then diode voltage will be Vs minus Vr minus VL. But at present, the diode voltage is actually Vs minus VL. There is no VR component and hence it experiences a spike in the turn on characteristics. The time it takes to turn on will be termed as forward recovery time. But the more important time in this case is the reverse recovery time, because that defines the switching time period of the devices, or that defines the switching frequency of the device. So I hope you got what is meant by reverse recovery. It means removing the stored charge near the depletion layer in order to regain the blocking capability. Now here I have magnified the reverse recovery characteristic. This is indicated by IRM, that is the maximum reverse current. So here that entire picture of the diode where we say that diode conducts in only one direction goes out of picture, because now the diode can conduct in reverse direction also. But remember, you cannot force it to conduct in the reverse direction. It is natural for the diode to conduct in a reverse direction for a short duration. It is, though it is undesirable, but it cannot be avoided, nor it can be controlled. It cannot also be controlled. Now if you see, the anode current reduces to 0 at this point. So from this point onwards, I will start to measure the reverse recovery time, because ideally the diode must have turned off at this point of time. Now this time when it reaches up to IRM is represented as TA, and when it reaches 25% of IRM is represented as TB. TRR is actually TA plus TB. Okay. We do not consider the case where it goes to 0, because it takes a long time to go to 0, as the current will decrease exponentially. So to become exactly 0, it may take infinite amount of time. So we define a threshold that is 25% of the IRM in order to have a finite value of the reverse recovery time. Now if we treat it as a triangle, then area under the curve of the current is actually charge. So reverse charge will be half IRM into TRR. Okay, that is area of this triangle. Now this is a straight line which will have a certain slope, that is di by dt. Now here it is 0 and here it is IRM. So delta y is actually minus IRM minus 0, that is final, or we can say, let us say IRM minus 0, because IRM itself is a negative value. Delta y is y final minus y initial upon t final minus t initial will be TA. Delta y by delta x. So this is di by dt is actually IRM by TA. So IRM can be written as TA into di by dt. Okay. Now if we say that TB is almost 0, or let me define TB by TA as S. This is called as softness factor or snappiness factor. So TB will be TA into 1 plus S. Sorry, TB is equal to TA into S. Now what will be the reverse recovery time? That is TA into 1 plus S, because it is TA plus TB. So now we can write IRM as di by dt into TA. TA will become TRR upon 1 plus S. If we substitute in the above equation, QR will be half di by dt into TRR square by 1 plus S. Now if TB is almost 0, that is S is almost 0, it is called as snappy recovery. That is, it recovers its reverse capability very fast. Okay, that means QR will become half di by dt into TRR square. That is called as snappy recovery or fast recovery diode. Okay. Now if the TRR is high, then what happens? The switching time is high, that means switching frequency will be low, or diode will operate slowly. So this reverse recovery characteristics are very important as from the perspective of diode. The only numerical problem in a diode can be framed from this topic. Now let me classify the devices. The devices, which are these devices? These are the diodes. So we divide these diodes into three categories. One is called as general purpose diode, other is called as fast recovery diode, and the last is Schottky diode. Now as the name suggests, general purpose diode is a normal diode, hence it will have a high reverse recovery time, which is almost 25 microsecond. Now as the name suggests, fast recovery diode recovers fastly, so it has a reverse recovery time of 5 microsecond. And in Schottky diode it is nanosecond. Now why does this difference arises in the reverse recovery time? That is due to construction of these devices. What is the difference in construction? In fast recovery diode, if we see the energy band diagram, this is my conduction band, this is my valence band. Here we do a doping of gold or platinum, due to which in the forbidden gap there are energy level. These are called as traps. Now as the name suggests, these will trap the charge carriers, that is either hole or a electron. Now if these will trap the charge carriers, then these will act as recombination centers. Okay. And to increase the depletion width, we need electrons and holes to recombine in order to generate ions. Okay. If they recombine, then the area will be depleted of the charge carriers. That means we need the charge carriers to recombine in order to regain the reverse blocking capability. Once the charge carrier recombine, the area will become depletion and the depletion width will increase, due to which reverse blocking capability increases. So since these provide the recombination centers, holes and electrons can easily recombine and hence reverse recovery will be faster, because now the holes and electrons will recombine faster and the diode will regain the reverse blocking capability. What happens in case of Schottky diode? In case of Schottky diode, we only have one type of semiconductor and then there is a metal. Now due to one type of semiconductor, there is no concept of the minority charge carriers. Only there are majority charge carriers. Now if there are no minority charge carriers, then you do not need to remove the stored charges in the device. And hence the reverse recovery time is very less. So it has the least reverse recovery time because there are no excess stored charge carriers, no need to remove them. So the reverse recovery time will be very less. Next is their rating. In case of general purpose diode, now remember, the faster a device, the lesser is the rating. As I told you in the earlier case also, minority carrier devices are usually slow but have higher rating, majority have lesser rating but high frequency. So if you increase the speed, then what happens? As you increase the frequency, switching power losses increase. That is why you have to operate them at a lower value of voltage and current. That means increasing the frequency leads to reduction in the rating. Remember, always the high frequency devices have lesser rating. So that is why this has a lesser frequency or more time. So its rating will be from ampere to kiloampere. Whereas in fast recovery diode, it is only up to hundreds of ampere, that is x into 100, where x is less than 10, 500, 400 like this, and it has a rating of only 300 ampere. Similarly, voltage rating is 50 volt to 50 kilovolt. Here the voltage rating is up to only 3 kV. Here only up to 100 volt. Now what is the purpose of general purpose diode? Where they are used? They are used in rectifiers, because the input to rectifier is always a 50 Hz supply. Fast recovery diodes are used in inverters and choppers because they operate at high frequency. Schottky diode are used in SMPS, which is a switch mode power supply, and it is alternate type of power supply which has higher efficiency. Okay, that is the difference between these three type of diodes. Usually the fast recovery diodes may be made of silicon carbide and they will have the gold or the platinum doping. Okay. So let me summarize what we covered in this lecture. We first saw the operation of power diode in forward bias condition and in reverse bias. In forward bias, I told you about the conductivity modulation. That is, when charge carriers will enter the drift layer, the conductivity will increase and resistance will reduce. Then we saw what is the purpose of drift layer, as well as we saw what are the characteristics of a diode. What was the purpose of drift layer? To increase the reverse blocking capability, as well as it increases the resistance, but that reduces due to conductivity modulation. Then we saw DC diode parameter, that is forward voltage, reverse breakdown voltage and the reverse saturation current. AC diode parameter, that is the forward recovery time and the reverse recovery time. And we saw that the charge in the reverse recovery region is equal to half di by dt into TRR square by 1 plus S, where S is the snappiness factor, that is TB by TA. We saw that the reverse recovery time determines the frequency of operation of the device. Lower the reverse recovery time, higher is the frequency of operation. Okay. In the next lecture, we will start with the most important power semiconductor device, that is the SCR or the thyristor. That is the major portion from where majority of the question from this chapter can be framed. Okay, that we will start in the next lecture. Hi guys, in the last lecture we covered the concepts of power diode. We saw that power diode is different from a signal diode in a certain manner that we introduce a n- drift layer. Now what was the purpose of this drift layer was to increase the breakdown voltage. How it increases the breakdown voltage? Because it increases the depletion width W. Since depletion width increases, the breakdown voltage also increases. Now, what happens is, due to this n- drift layer, due to lesser charge carriers, conductivity reduces. If conductivity reduces, the on-state resistance increases. Then we studied the phenomena of conductivity modulation, in which we read that this R-on will reduce by the process of conductivity modulation. How? When charge carriers will be injected from P region and N region into the drift layer, the charge carrier density will increase and the conductivity also increases. Then we compared the characteristics of the power diode and the signal diode, and we came to a conclusion that power diode has more voltage drop, that is around 0.8 to 1 volt. Okay, and it has a higher breakdown voltage as compared to a signal diode. Then we studied about the AC parameters of the diode, that was forward recovery. What was the forward recovery time? The time that it takes the voltage to fall below a certain level after the forward current flows. That is, after the anode current is established in the diode, the time taken by the voltage to reduce to a low value is your forward recovery time. Similarly, we saw reverse recovery time. Reverse recovery time was the time required by the diode to remove the stored charge carriers in the device. Okay, and we derived that the reverse recovery charge was equal to half di by dt TRR square upon 1 plus S, where S is called as snappiness factor or the softness factor, and it indicates how fast the diode recovers. Then we saw certain categories of the diode, that is general purpose diode, fast recovery diode, and the Schottky diode. And we saw in fast recovery diode we have gold or platinum doping, which causes trap levels in the energy band gap and can cause faster recombination. In Schottky diode we had metal semiconductor junction, due to which it was a majority carrier device, so no stored minority carriers and hence less reverse recovery time. In this lecture we will be starting our study about the silicon controlled rectifier, which is the most important device from the power electronics perspective. Now, first of all, let us understand few things about the silicon controlled rectifier. It is a bipolar and unidirectional switch. Okay. Now, it has a safe operating area of first and second quadrant, and it is a semi-controlled switch, because its turning on can be controlled but not the turn off. And then it has a rating of around 3 kiloampere, 5 kilovolt. Okay, that is, it has a very high rating. It has a low frequency. It is a minority carrier device. Now I told you how to recognize minority carrier device. It must have a PN junction. Now look at the structure of SCR. It has a 4-layer structure. P positive, which is also called as P emitter, N minus, which is also called as N base, P, which is also called as P base, and N plus, which is also called as N emitter. Now if you see, when the current will flow from anode to cathode, it will encounter consecutive P and the N regions. So it encounters PN junction. Hence it is a minority carrier device. And a thyristor is represented something like this, with a anode, cathode and a gate terminal. So it is a 3-terminal device, out of which anode and cathode are the main terminals, whereas gate serves as a control terminal. Okay. That is, by applying the signal at the gate, we can control the turn on and the turn off process of the SCR. Now here if you see, we have 3 PN junctions which have been named as J1, J2 and J3. So remember, the junction J1 is near to the anode, J3 is near to the cathode, and J2 is the middle junction. Now let us understand the VI characteristics of a SCR. Now there are 3 modes in which an SCR operates. First is called as your forward blocking mode. Now what is meant by forward blocking? That means SCR is forward biased by keeping anode to cathode voltage as positive, but still it does not conduct. That is, it is blocking in the forward direction, or it is blocking the forward voltage. Now how does this happen? Is this happens when we do not apply any gate current. So let me show you the structure of SCR. P positive, N minus, P, N plus. Okay. Now this is my gate terminal. This is the anode terminal. This is the cathode terminal. Okay. So now what happens if we forward bias the SCR? If we forward bias, we will apply a positive voltage at the anode and negative voltage at the cathode. Now suppose the anode is applied with a voltage of 50 volt and cathode with a voltage of minus 50 volt. That means as we go from anode to cathode, the voltage will reduce from 50 volt to minus 50 volt. Now let me assume some of the voltages at each and every section. Suppose this is the voltage 50, this is minus 50, this let me say 20, this let me say minus 30. Now if you see the junctions J1, J2 and J3, In J1, P region has higher voltage as compared to N region. So J1 will be forward biased. In J2, N region has a higher voltage as compared to P region. So J2 is reverse biased. Similarly, in J3, P region has higher voltage as compared to N. So J3 is forward biased. So that is the state of the three junctions J1, J2 and J3. If we represent each junction by a switch, then actually J1 is forward biased, so it will act as a closed switch. J2 is reverse biased, open switch. J3 is closed switch. Like this. This will be anode, cathode. This is my J2. That means the entire voltage drop or entire voltage of the SCR will appear across J2. Okay. So J2 has to handle the entire forward blocking voltage of the SCR as J1 and J3 are forward biased. Now until J2 becomes forward biased or it starts conducting in the reverse direction, current cannot flow in the SCR and hence IG will remain 0 until IA will remain 0 until J2 conducts. Now how to make J2 conduct? Now since J2 is reverse biased, if you make voltage AK greater than VBO, that is the forward breakover voltage. Forward breakover voltage means the voltage at which this J2 will break down. If J2 breaks down, then what happens? It starts conducting in reverse direction, that is from N region to the P region. Now if it starts conduction, then current will flow from the anode to the cathode. Okay. So then this diode, then this SCR enters forward conduction mode. Okay. When this J2 starts conducting, then it enters forward conduction mode, and this is one of the most undesired method of triggering or switching on the SCR because J2 gets breakdown, due to which it may also get permanently damaged. So it is not recommended that you switch on the SCR by applying a breakdown voltage. The other method is by application of the gate signal that we will see in the coming slides. How does gate signal help in turn on of the SCR? Okay, I hope this is clear. In this, it is important that you remember the states of different junctions when you turn on a SCR or when it is in the forward blocking mode. And remember, whenever we will trigger the SCR by means of a gate signal, that is, if Ij is not equal to 0, or we can say Ij is greater than 0, then, or let us say another condition also, and VAK is also greater than 0. Then diode will or SCR will enter forward conduction mode. In this mode, J1, J2, J3 all are forward biased. Okay, all the three junctions will be forward biased if you trigger the SCR using the gate terminal. Okay, now the other mode is called as your reverse blocking mode. Now what is meant by reverse blocking mode? It means it is blocking the reverse voltage, that is, you have reverse biased the SCR and it is not conducting any current. But as I told you, in a practical switch, what happens is small amount of current flows through the switch even when it is in the off state. Such current will be called as leakage current of SCR. Now let me again explain by means of voltage what will be the state of each junction. Now these are the four layers: P plus, N minus, P, N plus. This is my anode, this is my cathode, and this will be my gate. Now what happens is, if we reverse bias it, then VAK will be less than 0. So let me say I apply minus 50 here, plus 50 here, and then the voltages are given as minus 50, minus 10, 20, 50. Now if you see here, P plus region is at minus 50, whereas N minus is at minus 10. That means this junction J1 is reverse biased because P has a lower potential. If we see junction J2, P is at a higher potential than N. So J2 is forward biased. Similarly, if we see J3, P is at a lower potential than N. So J3 is reverse biased. So in this state, two junctions will act as open circuit and one junction will act as a short circuit. That is J1, J2 and J3. So that means the reverse blocking capability is handled by the two junctions, which are J1 and J3, and J2 acts as the short circuit. And whenever you will make VAK greater than mod VBR, that is the reverse breakover voltage, then it will start conducting from cathode to anode. Just like a diode, it will start conducting current from cathode to anode if it breaks down in the reverse region. That is why I am mentioning the magnitude of voltage must be greater than reverse breakover voltage in the negative region. That is, if reverse breakover voltage is minus 100, you have to apply minus 150 volt amount of voltage, whose magnitude is higher. Okay. So that will break down the junction J1 and J3. For some SCRs, actually, the forward breakover voltage is same as reverse breakover voltage. Such SCR are called as symmetrical SCR, where both the voltages are equal. If both are unequal, then it is called as asymmetrical SCR. Now, based on these three regions of operation, let me show you how the current varies as the voltage across the SCR changes. Now, this is the characteristic of SCR. On y-axis, we take the anode current. X-axis, we have actually anode to cathode voltage. Here, we have just mentioned VA because we are assuming that VK is 0. Now, initially what happens is, when you do not apply any gate signal, as you keep on increasing the voltage, the SCR is in forward blocking mode. So here we have mentioned forward blocking mode, and there will be small leakage current through the SCR. But as soon as you exceed the forward breakover voltage, then what happens? J2 breaks down. If J2 breaks down, the voltage drop across the across the SCR reduces, because now it starts conducting. So voltage drop suddenly reduces like this, and current then increases. Okay, then the current will increase. But if we apply the gate current, then what happens is your forward breakover voltage reduces. So this is for IG1, then IG2, then IG3. Let me remove this, then it will be more clear. IG1, IG2 and IG3. As you go on increasing the magnitude of the gate current, the forward breakover voltage will keep on reducing. That I will tell you later on how does this happen. But just now you have to understand what is the use of gate signal. It reduces the forward breakover voltage and then does allow the SCR to turn on. So turn on of the SCR is controlled by means of the gate signal. Okay. Similarly, in the reverse region, there is a small reverse current flowing. So it is in the reverse blocking mode. And as soon as you exceed the reverse breakover voltage, it will start conducting in the reverse direction, similar to your forward breakover. Okay. In forward breakover, as soon as you exceed the forward breakover voltage, it enters the forward conduction mode. Similarly, if you exceed the reverse breakdown voltage, then it breaks down and starts conducting in the reverse direction. We do not specify any special mode for this. This will just be called as breakdown of SCR. So in reverse breakdown, which junctions break down? J1 and J3. In forward breakover, which junctions break down? J2. Okay. So if you want to turn on the SCR, breaking down junction J2 is not a desired method. Somehow we have to do something so that J2 becomes forward bias and all the three junctions become forward bias so that they start conducting current. Now, here we define two terms. If you see in the curve, one is called as your latching current, other is your holding current. So holding current is basically the minimum anode current you see in the curve. And latching current is the current if we extrapolate this curve to intersect the y-axis. So if you see this, latching current is greater than holding current. Now what is the significance of latching current? It is the minimum anode current at which the SCR will turn on. That is, whenever this much amount of current is established in the SCR, then it will be latched into the on state. Now what is meant by latched? Latched means it will be staying in the on state all by itself. Now when we study latches in the digital circuits, What is the use of a latch? It stores certain state that is either 0 or 1. Similarly here SCR will save the on state. That is, it will stay on no matter whether or not gate current is present thereafter. Okay. So it will stay in the on state. That is called as latching into the on state. Whereas holding current signifies the minimum anode current that is required or the maximum anode current below which the thyristor will be turned off. Okay. That means whenever you will reduce anode current to below holding current, then it will turn off. So holding current is associated with the turn off process, whereas latching current is associated with the turn on process. So you have to reduce the anode current below the holding level to turn off the SCR, and you have to increase the anode current above the latching current to turn on the SCR. Usually latching current is around 1.3 to 3 times the holding current. The typical value that we take is 2.5 times the holding current. Now let us understand the significance of the gate signal. How does gate signal help the SCR to turn on? Now, when you apply a positive gate signal, that is Ij is greater than 0, then what happens? Holes will be injected into the junction J3. Now when holes are injected into the junction J3, what happens is J3 becomes more forward biased, or you can understand the depletion width of the junction J3 reduces. Okay, W means depletion width, because whenever you are injecting the charges, the depletion layer will also catch those charges. So depletion width will reduce, because what is in the depletion region? There are ions which do not have any charge carriers. So if you give them charge carriers, depletion width will reduce. Now if depletion width reduces, then the voltage across the junction J3 also reduces. Now if you reduce the voltage across the junction J3, then what will happen? Since VAK will be assumed as constant, the voltage across junction J1 will increase. Okay, if voltage across junction J1 increases, then it becomes more forward biased. If you increase the voltage across junction J1, it becomes more forward biased, so it injects more holes. Okay, number of holes increases. Number of holes injected from the P plus region into the N minus region. Since more and more holes are injected, but this N minus is a low doping, lightly doped region. Now if it is a lightly doped region, means concentration of electrons is very less. Okay, since concentration of electrons is less, maximum number of holes will not be able to recombine with electrons, and they will enter the junction J3, or they will enter the P base. Now if they reach the depletion width of junction J2, that means the depletion width will reduce. Why depletion width reduces? Because if you are injecting charge carriers into the depletion width, then depletion width always reduces. Remember this point whenever we forward bias any device or we inject charge carriers. Even if you bombard any junction with charge carriers, then the depletion width reduces. So here what happens is there is a flood of charge carriers coming from the P plus region, which are injected into the J2 depletion width, due to which depletion width of junction J2 reduces. And these will reach the P base, where they will be combining with these holes. That means overall the number of holes will increase. Some holes are coming from the gate terminal, some are coming from the anode. So overall the number of holes increases, which will further forward bias the junction J3. So here we again reach this point. So this entire process will repeat itself over and over again until the device turns on. So let me show you what is the cycle here. If you apply gate current, then what happens is junction J3 depletion width reduces, due to which junction 1 voltage increases, due to which number of holes increases, due to which this junction J3 depletion width again reduces. Because the number of holes injected will work as the gate current. they will work similar to the gate current and reduce the depletion width of junction J3. So that way more and more charge carriers will be injected into the junction J2, due to which the depletion width of junction J2 will go on reducing, and after a certain time J2 becomes forward biased. If J2 becomes forward biased, then all the three junctions are forward biased and SCR is in the forward conduction mode. So SCR will start conducting as soon as junction J2 becomes forward biased. Okay. So remember this point when we are covering the gate signal. That is how gate signal helps us turn on the SCR. Now let us understand thyristor in terms of combination of two transistors. Now let me break the thyristor. This is actually P plus region. This is N minus base. This is P base. This is N plus. This is P N minus. So if you see, this is your cathode, anode. This is your cathode and this is my gate terminal. Now if you see, this above part acts as a PNP transistor, which I have shown here. This is the emitter terminal which acts as an anode. This is the base which is your N minus layer, and this P region is the collector. And this NPN transistor is another transistor here. So this is the collector, cathode acts as the emitter, and this is the base. Now if you see, collector of first transistor is connected to base of second. Similarly, collector of second transistor is connected to base of first. So that is how two transistors are connected. So an SCR can be modeled as a combination of a PNP and a NPN transistor. Now let us see here how the gate current increases the anode current. Okay, how does gate current is responsible for increasing the anode current? Now here by KCL, since we have three terminals, I can write entering current, that is IA plus IG, should be equal to leaving current, that is IK. So this will be universally true by the conservation of charge. Since charge can neither be created nor be destroyed, the current will be following the KCL. Now if you see here, the base current of first transistor is same as collector current of second. So IB1 is equal to actually IC2. Now IG is plus IC1 should be equal to IB2 from here if we apply KCL at this node. Now what is the relation between the collector and the emitter current? Actually this is the transistor Q1, this is Q2. If we see for Q1, IC1 is equal to alpha 1, emitter current is IA, plus ICBO1, that is the collector to emitter current with base open. For Q2, IC2 is alpha 2 into IK plus ICBO2. Now if we add these two currents, IC1 plus IC2, it will be alpha 1 plus alpha 1 into IA plus alpha 2 into IK plus ICBO1 plus ICBO2. Now IC2 is actually IB1, which is actually equal to IE1, that is IA. So it will be alpha 1 into IA. Let me replace IK by also IA. Alpha 2 into IA plus IG plus ICBO1 plus ICBO2. So that gives us an equation in IA and IG. So let me simplify this equation. Collecting all the IA terms on the left hand side, IA 1 minus alpha 1 minus alpha 2 is equal to alpha 2 into IG plus ICBO1 plus ICBO2. That means IA will be equal to alpha 2 by 1 minus alpha 1 minus alpha 2 IG plus ICBO1 plus ICBO2 by 1 minus alpha 1 minus alpha 2. Okay. So that way, by introducing the gate current IG, our anode current increases. Okay. If you reduce Ig to 0, anode current will be very less. That will be equal to the leakage current. Now, let me explain qualitatively how the introduction of Ig causes the SCR to be turned on. So here if we apply Ig, it will cause Ib2 to increase. If the base current increases, the collector current will increase automatically because IC upon IB is beta. Now this is also equal to IB1, which also increases, which increases IC1. Now if IC1 increases and also IE1, which is equal to IA, also increases. If IC1 increases, then IC1 plus IG, that is equal to IB2, increases. So this will be a cyclic process. So the SCR will be latched into the conduction state. This is a regenerative process that will keep on repeating itself. That I explained you by means of the charges injected at the gate also, and also I explained you in terms of the two transistor analogy. So here you must always remember this is a regenerative process by which the SCR will turn on. Now let us understand the significance of latching and the holding current. Basically, what is the latching current? It is the minimum anode current above which only it will turn on. That is, when IA will be equal to IL, then only SCR will turn on. So you will have to apply the gate pulse until and unless IA becomes equal to IL. Till then you cannot remove the gate pulse. So till then Ig will be non-zero. So it gives us a measure of minimum pulse width. That is, what is the minimum time for which the gate current must be applied in order to turn on the SCR. That means pulse width must always be greater than T on minimum. That is how this gives us an important design parameter of the gate drive circuit. Whatever circuit is driving the gate terminal must generate a gate pulse of width more than the minimum pulse width. Similarly, holding current is related to the turn off process. You have to reduce anode current below the holding current in order to turn it off. But SCR cannot be turned off by the gate signal. So we have to use an additional circuit or external circuit which is called as commutation circuit. What is the rule of this commutation circuit? It will reduce the anode current to below the holding level. Actually, the commutation circuit performs two functions. The first function is reduce the anode current below the holding level. The second function is to reverse bias the SCR to remove charges or to remove excess charge carriers. Like I told you, in the case of diode, there is a reverse recovery process in which we remove the excess stored charge carriers. Similarly, here we will remove the excess stored charge carriers by which that SCR will regain its blocking capability. So turn off process involves these two phenomena. Now here also this will be termed as IRM, that is the maximum reverse current, and this will be 25% of IRM. So this time will be TRR. Here I am assuming holding current is 0. So whenever anode current is reduced to 0, the turn off process will start, or you will reverse bias the SCR only when the anode current reduces to 0 or below the holding level. Now this period additional is called as TGR, that is the gate recovery time. In this time, the charges stored near the gate junction are removed. In TRR, we will remove the charges stored in the outer junctions, and in TGR, we will remove the excess stored charge carriers in the gate. This entire time is called as TQ. TQ is called as device turn off time. It is the time required by the SCR to turn off. You have to give it more than this time, otherwise it will fail to turn off. If it fails to turn off, then there is excess charge carriers. Okay. Stored charge carriers are non-zero. So whenever you will apply VAK, these stored charge carriers will act as a gate current and SCR will turn on, which is undesirable. That is, as soon as you apply the forward voltage, the SCR will turn on. You will lose the control over the turn on process of the SCR due to the stored charge carriers. This process is known as commutation failure. Okay. If you do not give it enough time, then stored charge carriers will not be removed completely, due to which it will not be able to turn off properly, and these stored charge carriers will work as the gate current in the next cycle and cause unwanted turn on of the SCR. So the device turn off time is TRR plus TGR, gate recovery plus reverse recovery. Now what is the circuit turn off time actually? It is the time given by the commutation circuit to turn off the SCR. Time for which SCR is reverse biased by commutation circuit. Now we know the minimum time for which SCR must be reverse biased is TQ. Okay, minimum is TQ. So you have to reverse bias it for greater than equal to TQ time. So the actual time for which it is reverse biased is represented by TC, that is circuit turn off time. It must be greater than equal to TQ. Okay, for the successful commutation. If TC is less than TQ, then stored charges will not be removed completely and it will be commutation failure. So whenever we are designing the commutation circuit, the first objective is to keep circuit turn off time greater than the device turn off time. So we have to design suitably so that device turn off time is not, or circuit turn off time is not less than device turn off time. Actually the ratio of circuit turn off time to device turn off time is called as safety factor. So we will keep TC greater than TQ, that is why safety factor will be greater than 1, and usually safety factor is kept at 2. So we will keep the circuit turn off time twice the device turn off time. So let me summarize what we covered in this lecture. We saw the SCR structure, then we saw the forward blocking mode. What was the state of junctions? This was forward bias, reverse biased, forward biased. Then we saw forward conduction mode, that is achieved by either keeping VAK greater than VBO or by introducing the gate current. So this was forward biased, this was forward biased, this was forward biased. Next we saw reverse blocking. In this, these were reverse biased outer junctions and inner was forward biased. Then we saw that for symmetrical SCR, VBO is equal to VBR. Then we saw what is the significance of gate signal. I told you it injects the charge carriers which forward biases the junction J3, which will forward bias the junction J1 and still increase the charge carriers. So this will be a repetitive process and charge carriers will go on increasing. Then we saw two transistor model in which we replace the SCR by means of two transistor NPN and PNP. There we saw IA is equal to IG alpha 2 over 1 minus alpha 1 minus alpha 2. Alpha 2 is the gain of transistor Q2 or NPN transistor plus ICBO1 plus ICBO2 by 1 minus alpha 1 minus alpha 2. Then we saw the concept of the reverse recovery or the circuit and the device turn off time. So we saw that TC is always greater than TQ. This will be used when we will study the commutation circuits of the SCR. Okay. So in the next lecture what we will see is, we will see the switching characteristics of the SCR and we will see how to turn on the SCR. What are the desirable methods by which we can turn on? Because increasing the anode to cathode voltage greater than breakover voltage is a undesirable method. Hi guys, in the last lecture we started with the concept of SCR. We saw that SCR was a 4-layer device, that is PNPN, in which one terminal was gate, one was anode and the other was cathode. So in the last lecture what we saw about SCR was, we saw the operating modes, that is forward blocking mode, forward conduction mode and reverse blocking mode. We saw that in forward conduction mode all the three junctions were forward biased. In forward blocking mode the central junction was forward biased. The central junction was reverse biased and the other two junctions were forward biased. And in the reverse blocking mode the outer junctions were reverse biased and the inner junction was forward biased. That we saw in the last lecture. Then we saw the VI characteristics, in which we observed that if we increase the gate current, then the forward breakover voltage reduces. Then we saw how gate signal reduces the forward voltage by injecting charge carriers and increasing the number of holes injected through the junction J3, and thus it decreases the depletion width of J3 and the voltage drop across J3. So J1 becomes more forward biased and sends more number of poles, which along with the gate current will constitute higher number of holes, and hence the number of holes in the device will increase and the biasing of J3 again increases. So it follows in a cycle and the SCR is latched into on state. Then we saw two transistor model of the SCR. We saw that SCR can be replaced by two transistors, one NPN and other is the PNP type of transistor. Then we saw latching and holding current. And the last we saw was the role of commutation circuit. Okay, so this is what we covered in the last lecture. So in this lecture what we will focus on is, we will focus on the different type of triggering methods that are used to trigger the SCR. First let us understand the dynamic characteristics of the SCR. So in dynamic characteristics there are two type of characteristics, basically turn on and turn off. The turn off characteristics are similar to case of diode. That is, we will have a reverse recovery type of characteristic, that is TRR, which was equal to TA plus TB. But here, as I told you in the last lecture, we also have TGR, and TRR plus TGR combinedly is called as TRR plus TGR combinedly is called as device turn off time. And I told you for successful commutation, circuit turn off time must be greater than or equal to device turn off time. In the turn on transition, we usually define three times: delay time, rise time and spread time. So let us understand each time in detail. So the first time that is studied is delay time. Now in delay time, what is meant by delay time? Ideally, whenever I apply the gate current, the thyristor must turn on. So the delay is the time between the application of gate signal to the time when the anode current becomes 10% of the final value. That is, anode current begins to increase. That will be termed as your delay time. So whenever gate current is equal to 0.9 Ig to the time when anode current is equal to 0.1 Ia. This is called as your delay. Okay. Now this delay will depend on the magnitude of gate current and the rate of rise of gate current. The thing is that the gate current will not be constant. It will also increase gradually. So it depends how fastly the gate current is increasing, because the faster gate current increases, the more number of holes and electrons it injects into the system, and hence the faster device turns on. So actually dig by dt and ig will reduce the magnitude of the gate current required to turn on the SCR. Okay, they will actually make the turn on process faster and thus reduce the delay time. So that is your delay time. And delay time always depends on the initial conduction area. Actually what happens is, when gate will inject the charge carriers, they will spread into a certain area that is called as initial conducting area, and they will make that region conducting. So whenever the anode holes will enter the cathode, they will flow through that area. So higher is the initial conduction area, more number of holes can flow from anode towards the cathode, and hence the current will increase. Okay, so that is, the delay time also depends on initial conduction area. Higher is the initial conduction area, lesser will be the delay time. So if you increase initial conduction area, then delay time reduces. If you increase Ig, delay time reduces. If you increase dig by dt, delay time reduces. So these are some methods by which we can reduce the delay. And ideally reducing the delay is very important because we want the operation to be faster. The next time that we studied is rise time, which is represented by TR. It is the time when anode current rises from 10% of IA to 90%. In classical control theory, what we study is the rise time can be defined from 5% to 95% or from 10 to 90. So here we are following the convention of 10% to 90%. And also the anode voltage will drop from 0.9 VA to 0.1 VA. So we are assuming both the processes are simultaneous. As the voltage reduces, the current through the device increases. So the voltage must go from 90 to 10% and the current must go from 10% to 90%. That will be called as your rise time. Now in rise time, the losses in the circuit are very high because VA is not equal to 0, IA is not equal to 0. So most of the switching losses will occur during the rise time. Okay, because switching losses will occur during the turn on transition, that is when the switch turns on from the off to the on state, and even inside of that the maximum losses will be occurring at the rise time. Okay, and now what does rise time depend on? Rise time depends on the load inductance. If you increase inductance, then dia by dt reduces, and due to which dr increases. Why di by dt reduces? Because dia by dt is equal to v by L. If L increases, di by dt reduces. The next is your spread time, that is Ts. Now, when the charge carriers are injected from the anode, they will take certain time to spread through the entire area. So the time taken by the charges to spread through the entire conduction area of the device is termed as your spread time. Okay, it is the time taken to spread. In this, the current goes from 0.9 IA to IA, and voltage goes from 0.1 VA to 0. So that is what happens during the spread time. Now if spread time is not small, then the current will be concentrated into a smaller area for a longer time. If you do not have initial conduction area, or you do not have enough conducting area, then current will be constrained to a smaller region, due to which there will be losses in that region and temperature rise. So that is caused as the problem of local hotspot. Okay, because locally there will be some spots which will be hot due to higher losses in that region. So how to avoid it is, to avoid this we must reduce the spread time of the device. Okay, Now spread time depends on actually geometrical construction of the device. If you construct the device in such a way that the spreading of the charges is easy, or charges find multiple paths to spread through the device, or we have a multi-gate structure where there is more than one gate, so that it helps the transistor to inject the charge carriers in a better way, and hence it makes our task easier. So geometrical construction determines what is the spread time. So let us see the dynamic characteristics being plotted here. So here the gate current gradually increases. We are interested when the gate current goes to 90%. So this will be our reference. So after gate current goes 90% and anode current becomes 10%, this time will be measured as delay time. Now when anode current goes from 10 to 90%, it will be rise time. 90 to 100 will be spread time. Similarly, the voltage will go from 100 to 90, 90 to 10, 10 to 0. So T on turn on time will be delay plus rise time plus spread time. To reduce the turn on time, we can reduce either component of the turn on time, and by reducing turn on time, we can increase the frequency of operation of the device. Okay. In the reverse, as I told you, there is no need to explain. TQ is TRR plus TGR, reverse recovery time plus gate recovery time. In gate recovery time, we remove the excess charge carriers stored near the gate junction. Now let us see, as I told you, increasing the forward voltage above the blocking voltage is not desirable method for turn on of a SCR. Let us see what kind of methods can we implement to turn on the SCR. So the first method is called as forward voltage triggering. Now what is meant by forward voltage triggering? Whenever VAK is greater than VBO, junction J2 breaks down and conduction starts. As I told you, this is the most undesirable method for starting the conduction of a SCR. Why? Because it involves a junction breakdown. If junction continuously breaks down after regular intervals, then after certain time it will get permanently damaged and it will not be able to allow any current. Okay, so that is why that junction can get destroyed. So this is not a reliable method of triggering. The next triggering method is called as dV by dt triggering. Now understand, whenever a depletion width is formed in a device, so here we had negative ions with holes. Here we have only negative ions. They are depleted of any charge carriers. Here we have positive ions. Here we have positive ions with electrons. Now if you see this region, this depletion region, here positive and the negative charges are separated by a distance. Hence it forms a capacitance, which under reverse biasing is known as junction capacitance. Okay. So this junction capacitance is formed due to separation of charges in the depletion region. That means whenever the current is flowing from anode to cathode, the small leakage current will act as the line charging current because it is specifically being drawn by the capacitor. Though we may know it or not, but it is being drawn by the capacitor. So it will be the line charging type of current. Now, here I have shown the junction capacitance Cj, it is due to the junction J2, and Ic, that is the charging current, will be equal to Ia. Now, if this charging current exceeds the latching current, then this SCR will turn on. If Ic is greater than I latching. That means what is the critical value of dV by dt? So dV by dt critical will be equal to latching current by C. So dV by dt must be greater than or equal to the critical value in order to turn on a SCR. High dV by dt ensures high line charging current, and high charging current ensures higher amount of anode current, which when exceeds latching current will cause the SCR to turn on. Okay, so that is also a undesirable method, because here the device is turning on all by itself. Next is your light triggering. What happens is, to decrease the depletion width, we need to generate electrons and holes. So what happens in the depletion region is, this negative ion with a hole will gain an electron and it will become a negative ion. Similarly, positive ion with an electron will donate an electron, it will become positive ion. So that is, if you wish to make them again a part of the p region and the n region respectively and reduce this depletion width, then you will have to generate the charge carriers, because depletion width is generated due to removal of the excess charge carriers. Now if you want to generate the electrons and the holes in the depletion region, then one method is incidenting the light of a suitable frequency. If h nu is greater than ionization energy, then what happens? Electrons and holes will be created in the junction J2, due to which these will start conducting and reduce the depletion width of junction J2. Okay, it will generate electron and hole, which will reduce the depletion width of junction J2. If depletion width reduces, then anode current increases. So that is how we can trigger the SCR by means of a light. This is one of the desirable method. Why desirable? Because the light source is not actually connected to the SCR. The light source can be incident, or it can be incident from a farther distance. Since it is not directly connected to SCR, the chances of this getting damaged due to high current carried by SCR chances are none. Why? Because both are isolated from each other. So whenever we are talking about triggering the SCR, electrical isolation becomes one of the major factors, as the control circuit must not have anything in common with the power circuit. If they have something in common, then due to high current in the power circuit, the control circuit can get damaged. So in light triggering, automatically there will be a isolation. So it is also used to trigger the multiple number of SCR simultaneously, because it will depend on which SCR you are triggering the light. So that is a desirable method of triggering. The next method is the thermal triggering. Now to generate the charge carriers in the junction J2, if we heat J2, then what happens? Thermal energy, that is 3 by 2 kT, will increase. If this thermal energy increases, electron and holes are generated in the junction J2. If these are generated, then the depletion width of junction J2 reduces, due to which anode current increases. But this is also an undesirable method, heating the junction J2, because this can cause thermal damage to the SCR. We cannot just heat up the device. That is why thermal triggering is very rarely used. So actually what I am trying to do is, I am just trying to create enough charge carriers in the depletion region of junction J2 so that it becomes conducting. The final method that comes is the gate triggering method. That is, by applying the gate current, we can reduce the forward breakover voltage and can cause the SCR to turn on. This is the most popular method of turning on the SCR. Now gate triggering method can have different categories. So the first part is, or the first category is, continuous gate signal. Now in continuous gate signal, what we do is, we continuously apply Ig, which is non-zero. That is, it will be applied indefinitely. But as we know, once the SCR turns on, the gate loses control. That means the gate current is no longer required once the SCR is latched into the conduction state. If gate current is no longer required but you are still keeping Ig non-zero, then the losses in the gate drive circuit, that is Ig square Rg, will be high, which is not desirable, which is undesirable. Hence, we can make the gate current 0 as soon as the device is latched into the conduction state. That brings us to the next type of gate triggering, that is the pulse triggering. In pulse triggering, actually, we apply a pulse of short duration at the gate terminals. That is like this. Since the operation is periodic, we will have to apply this pulse periodically. Here T1 is the width of the pulse, T is the switching time period. So actually T1 upon T1 T minus T1, this is called as mark to space ratio. Why mark to space? Because wherever Ij is high, it represents a mark. Wherever Ij is 0, it represents a space. So mark to space ratio. Similarly, T1 upon total time T is called as duty cycle. That is, what is the fraction of the total time period for which the Ig exists. That is called as duty cycle. So pulse triggering will reduce the losses, and here the width of the pulse must be greater than the minimum pulse width. I told you minimum pulse width is derived from the latching current of the SCR. Whatever is the latching current, higher the latching current, higher will be the minimum pulse width. So T1 should be greater than the minimum pulse width so that SCR can be turned on. Next method is a high frequency pulse triggering. That is, we will apply the pulses but they will be high frequency. Now what is the purpose of high frequency pulses is this pulse transformer. As we have studied, size of machine is inversely proportional to frequency. So size of pulse transformer reduces. What is the use of pulse transformer? As I told you, always there must be electrical isolation between the gate circuit and the power circuit. To provide that isolation in electrical domain, we connect a transformer. So by the use of high frequency pulses, actually the size of pulse transformer reduces, which reduces our design criteria. So it makes the firing of the thyristor or triggering the SCR easy. So let me summarize what we covered in this lecture. We first saw the dynamic characteristics, in which we saw on time is equal to delay time plus rise time plus spread time. Delay time was the time taken by the SCR in which the anode current rises from 0 IA to 0.1 IA after the gate current reaches 0.9 of its maximum value. Then rise time was the time taken by the device to make the anode current increase from 10% to the 90% and anode voltage to fall from 90% to 10%. And last was the spread time, that is the time taken by the charge carriers to spread throughout the device. In this, the anode current rises from 90% to its 100%. Then we saw different triggering method. First we saw forward voltage triggering. That is when VAK is greater than VBO. It is undesirable method. Then we saw dV by dt triggering. That is, we saw if dV by dt is high, then the charging current of the capacitor or the junction capacitor is high, and if C dV by dt is greater than I latching, then it will cause the thyristor to turn on. Then we saw light triggering. That is, we were creating the charge carriers in the junction J2 by incidenting the light of a suitable frequency. Then we saw thermal triggering, in which we heated up the junction J2 in order to create more charge carriers. And last we saw gate triggering, in which we applied the gate signal in order to turn on the SCR. In gate triggering we saw three: continuous gate current, in which the losses were high; then pulse gate current, in which the size of pulse transformer was high; and then the high frequency pulse triggering, in which the size of pulse transformer is reduced. So in the next lecture we will see what kind of circuits can we design in order to trigger the SCR. That is, we will see about the firing circuits of the SCR. Hi guys, in the last lecture we saw the dynamic characteristics of SCR. In dynamic characteristics we mainly focused on our turn on characteristics. In turn on characteristics we saw turn on time was delay time plus rise time plus spread time. The delay time was the time required for the anode current to rise to the 10% of its maximum value after the gate current reaches 90% of the maximum value. Rise time was the time taken by anode current to rise from 10% to the 90% of its final value. And spread time was the time taken by anode current to reach a maximum value from the 90% of the maximum value. So, delay time depended on the rate at which the gate current rises and the magnitude of gate current. Rise time depended on the load parameters and spread time depended on the geometric construction of the device. Then we moved on to the triggering methods of SCR. We saw various triggering methods. The first was the forward voltage triggering method, in which we apply a forward voltage greater than forward breakover voltage to trigger the SCR. Then we saw the dV by dt triggering method, in which if C dV by dt is greater than latching current, then SCR is triggered. But both these methods are, if C dV by dt is greater than latching current, then SCR is triggered, but both these methods are undesirable methods. Then we saw light triggering, which was a desirable method as it can trigger multiple SCRs simultaneously and it provides isolation between the control and the power circuit. Then we saw thermal triggering, in which we heated the junction J2 in order to create electrons and holes in the junction J2 and reduce the depletion width. This is also an undesirable method because it can cause thermal damage to the SCR. Then we saw gate pulse triggering, in which we saw three categories. One was the continuous gate pulse, but that had a disadvantage as the gate losses were very high. Then we saw the pulse gate triggering, in which we applied a pulse greater than the minimum pulse width, but the disadvantage was size of the pulse transformer was high due to low frequency. And then high frequency gate pulse triggering, in which we applied multiple pulses having high frequency. It had the advantage that the size of pulse transformer reduced. What is the pulse transformer? It is a 1:1 transformer which transforms the pulses in order to provide electrical isolation between control circuit and the power circuit. In this lecture, what we will say is, we will look at the firing circuits that are generally used to trigger the SCR. First firing circuit is the resistance firing circuit. Now this is the simplest of all the firing circuit as well as most economical. Now here there are limits always imposed on the gate current as well as the gate voltage. That is, gate current should always lie between the minimum and the maximum value. Similarly, gate voltage must also lie between minimum and the maximum value. Now there are certain resistances here, R1, R and R2. What is the purpose of each and every resistance? First let us see R1. What is the purpose of resistance? This is the voltage Vs. Vs will be equal to Vm sin omega t. Now suppose if load is 0 as well as this resistance is also 0, then maximum value of gate current is Vm by R1. Okay, so we want that Ig max should always be greater than or equal to Vm by R1. That is, the actual value of maximum gate current should be less than this limit. Is it fine? The maximum value of gate current in this circuit possible is Vm by R1, but it should always be less than the maximum capability of the SCR. That is, R1 should always be greater than or equal to Vm by Ig max. Okay. Similarly, what is the purpose of R2? Now, the purpose of R2 is to limiting the gate voltage. Like R1 limits the gate current, R2 limits the gate voltage. Now, what is the Vg max? The maximum voltage across gate will be Vm into R2 by R1 plus R2. This should be, or let me say Vmax instead of Vg max to avoid confusion. This should always be less than equal to Vg max. Okay, that is, the maximum gate voltage produced by this circuit should be less than the maximum limit of the gate voltage. Then what is the purpose of this R? The purpose of this R is to provide the control and hence change the firing angle. Now what is a firing angle is? A firing angle is defined as the angle at which a SCR is triggered after it is forward biased. Now suppose the SCR becomes forward biased, that is, the voltage across SCR becomes greater than 0, let us say at 30 degree, but you provide the gate pulse at 60 degree, then firing angle will become 30, because after forward biasing, after a delay of 30 degree, you are triggering the SCR. So it is the delay between the point of becoming forward biased and the point of applying gate pulse. The difference between the two is called as your firing angle. So to provide control, we need to vary the points at which we can trigger the SCR. That is what is meant by controlling the SCR. So we need to control the firing angle of SCR. Because if SCR switches on as soon as it is forward biased, then it is nothing more than a diode. Because as soon as the diode becomes forward biased, it turns on. But we want to control the SCR and hence we want to control the firing angle. So now let us see how does the firing angle is varied. Actually, the gate voltage will be given as supply voltage, and by applying potential divider R2 over R1 plus R plus R2, that is Vgm sin omega t. Now what is this Vgm? It is Vm R2 over R1 plus R plus R2. So that is, by varying R or by increasing R, we can decrease the value of Vgm. As R increases, Vgm reduces. Now we put a threshold condition in the SCR that if Vg is greater than Vg threshold, then SCR turns on. Okay. So now let me show you in terms of a graph how does the SCR turns on. Suppose this is my sinusoidal voltage. Now, when this is equal to like VGT, then this part will be my firing angle. Let us say this is VGA, this is alpha A. Okay, and it is equal to, it is when R is equal to RA. Now suppose we increase the value of R, that will decrease the value of maximum voltage. So it will be something like this. Now the intersection is coming here. So this will be alpha B. This is for R is equal to RB, where RB is greater than RA. So as you increase the resistance, the value of firing angle increases, because the SCR becomes forward bias as soon as voltage becomes positive, but you are triggering it at an angle alpha A and alpha B. So these are the firing angle. If you increase it further, then at the most this can be like this. This is for RC, which is greater than RB, greater than RA. Here the firing angle is at 90 degree. If you increase the resistance any more than this, then we won't get any intersection. So that means the maximum value of firing angle with this circuit is 90 degree. It is when the curve is tangential to the VGT. If you go beyond that, then they won't have any intersection and the SCR will not be triggered. So what happens at the firing angle is VGM sin alpha becomes equal to VGT, due to which alpha is equal to sin inverse VGT by VGM. So that is the firing angle at which the SCR will be triggered. If we increase resistance, then firing angle also increases. So the advantage of this circuit is it is economical as well as it is simple, but the disadvantage is it can only provide firing angle up to angle 90 degree, not more than that. So now let us look at another circuit which can remove this limitation. That is called as the RC firing circuit. Now here this R component and the C component, they form the firing circuit, and this full wave rectifier or full bridge rectifier and this load, these are the power circuit. Okay, so these are not the part of the triggering circuit of the SCR. Now what happens in the RC circuit is, in RC circuit, whatever is the current will always be leading the voltage. So what will be the current in the RC circuit? It will be Vm by mod Z sine omega t plus phi. I am assuming that the source is Vm sine omega t. That means it is leading the voltage by an angle phi, where phi will be equal to tan inverse xc by r, that is tan inverse 1 by omega r c. Now for applying the gate voltage, we need to calculate the voltage across capacitor. Vc will be I into minus jxc, that is Vm xc by mod z, then shifted by an angle 90 degree, omega t plus phi minus 90. Now usually phi will be less than 90, so this can also be written as Vm xc by mod z sine omega t minus 90 minus phi. That is, this voltage is shifted towards right by an angle phi. So let me show you how it triggers. Again the condition here will be whenever Vg is greater than Vgt, the SCR is triggered. So Vg is actually Vm xc by mod z. Now if you see here, first let me draw the supply voltage. The supply voltage will be something like this. Now this voltage or the gate voltage will be lagging it by an angle 90 minus phi. And the amplitude will also be lesser like this. Okay. Now let me draw the threshold voltage. This will be my threshold voltage. Now wherever these two curves intersect, this will give me a firing angle. Now if you increase the value of resistance, then what happens? Mod Z increases. Then what happens? VGM reduces. That is the maximum value of gate voltage reduces. So let me draw another curve, and also the phi will change. So what will be the effect of phi? Effect on phi as R is increased, phi reduces as R increases. So 90 minus phi increases. So the lag will also increase. So how it will be? Like this. So now here we are getting this as the firing angle alpha 2. Now if you see, this is the 90-degree point. So here we can get alpha 2 greater than 90 degree. So here the value of firing angle can be greater than 90 degree. Is it fine? So that is how this circuit removes the limitation imposed by the resistance firing circuit. Here we can easily achieve the firing angles greater than 90. Is it fine? Because what we want is, we want that we should have control over the firing angle from 0 degree to 180 degree. So these are the two simple firing circuits that are used to trigger the SCR. The third and the most popular circuit is the uni-junction transistor, also called as UJT. Now what is the basic structure of UJT is? It is a PN junction PN. This is our emitter terminal. This is base 2. This is base 1. Now what happens is, whenever there is a PN junction, there will be some depletion width. Now between B2 and B1, it is only a N-type semiconductor. So it will behave as a resistance. Simply a N-type semiconductor will behave as a resistance. Now if the depletion width will increase between the P and the N junction, then it will cause an hindrance to the current flow. So if you apply emitter voltage less than 0, then depletion width increases and current reduces. Now there will be some voltage of emitter at which the entire region is depleted, which causes current to be 0. If let us say V is equal to VE critical, then depletion width is equal to width of the device and I becomes 0. This is called as the pinch off voltage, where the channel is pinched off or there is no channel between the two base terminals. But if we apply V greater than 0, then the depletion width reduces and current will increase. Is it fine? So that is the basic principle of the working of uni-junction transistor. Here why it is called as uni-junction? Because there is only one junction between the P and the N regions. Okay. So why we go for uni-junction transistor instead of the resistance firing circuit or the RC triggering circuit? The simple reason is that in resistance and the RC firing circuit, we had the resistances. In case of resistances, there will be power loss in the firing circuit. And due to prolonged power loss, then the power loss will be very high and the efficiency will be low. That is why it is preferable to use uni-junction transistor instead of the resistance or the RC firing circuits. Now the circuit equivalent or the electrical equivalent of a UJT is shown here. It is represented like this, but usually this emitter is represented by a curved arrow to differentiate it from the JFET, okay, instead of the straight line. Now we represent a diode between the emitter and the base terminal because there is a PN junction, and between the base 2 and emitter there is a resistance, and between emitter and base 1 also there is a resistance. So that means this resistance R is divided into two parts, that is base 2 to emitter and base 1 to emitter, RB2 and RB1. Okay, so that is how the electrical equivalent of a UJT looks like. Now when the diode is off, suppose diode is off, then what is the voltage across RB1? That will be VBB into RB1 over RB1 plus RB2. What is this VBB voltage? This is the voltage applied to B2, that is VBB. By potential divider simply I have calculated the voltage across RB1 when the diode is in off state. So we call it as eta VBB, where what is the eta? Eta is the RB1 over RB1 plus RB2. It is called as intrinsic standoff ratio, okay, because these resistances RB1 and RB2 are intrinsic resistances and are not connected externally. So hence it is called as intrinsic standoff ratio. Now the maximum value of emitter voltage can be eta VBB plus VD. Why is this the maximum voltage or the peak voltage? Because once the emitter voltage exceeds this amount of voltage, then diode will turn on. And if diode turns on, then it starts conducting. Now one of the properties of UJT is whenever UJT is turned on, then due to negative differential resistance, this RB1 reduces very steeply. RB1 reduces very fast. It has a negative resistance character or negative differential resistance, which means the resistance reduces as the voltage is increased. If resistance reduces, then this emitter voltage will also fall down, because emitter voltage is voltage across RB1 plus VD. So emitter voltage also falls down as UJT turns on. Why the resistance decreases? Remember, it has a negative differential resistance. Okay, and whenever emitter voltage falls below the valley voltage, then UJT turns off. So to turn it on, emitter voltage must be greater than VP, that is the peak voltage. To turn it off, it must be less than valley voltage. This valley voltage is a device manufacturer specification. Okay, it is always specified by the manufacturer what is the minimum voltage below which the SCR will be turned off. Now this is how the characteristics of the SCR will look like. Initially the voltage will keep on increasing, but as soon as it reaches the peak point, then due to negative resistance, RB1 will reduce, due to which the emitter voltage, which is equal to VBB RB1 upon RB1 plus RB2 plus VD, will also reduce as RB1 reduces. So though the current increases, but this voltage goes down, and as soon as it reaches the valley point, it will turn off and then it will enter saturation mode. Okay, saturation means the channel width is so minimum that the current will not increase rapidly in the UJT. Okay, that is the characteristics of the UJT. Now the resistance RE, that is series resistance with emitter. Okay, whenever we are using UJT in the circuit, we will connect a resistance in series with the emitter. This must always lie between the two limits VBB minus VP by IP. Okay, these are the two limits between which this resistance must always lie. Now, how to trigger the SCR using the UJT? That is the main problem. To trigger the SCR using UJT, we have to make a relaxation oscillator using the UJT. Now, this is the basic circuit of constructing relaxation oscillator from UJT. Here we have a RC circuit, and these two are the external resistances R2 and R1. The internal resistances are always RB2 and RB1. Now what happens is, whenever this UJT is turned, whenever this circuit is switched on, then due to this RC circuit, the capacitor starts charging. Now what is the equation of capacitor charging? VC will be VBB into 1 minus e raised power minus t by RC. Now whenever this capacitor voltage is actually equal to emitter voltage, whenever it is greater than eta VBB plus VD, then this UJT turns on and its resistance reduces and it starts conduction. Then this capacitor will start discharging. Now as soon as the capacitor voltage will fall below the valley voltage, the UJT will turn off and the capacitor will again start charging. So it will be a periodic phenomena in which first the capacitor charges and reaches the peak voltage, then UJT turns on, then capacitor discharges, reaches the valley voltage, UJT turns on, capacitor starts charging again. So here initially the UJT was off, capacitor was charging. Now it charges up to this point, peak voltage, then UJT turns on and capacitor starts discharging. As soon as it reaches valley voltage, UJT turns off, it starts charging again. So this will be the capacitor voltage. Out of this waveform when UJT is on, this part is used for triggering the SCR. This will be connected to the gate terminal of the SCR. So that is how we trigger the SCR using a UJT. That is a UJT relaxation oscillator. Now what is the time period of the pulse? It is RC ln 1 upon 1 minus eta. This is an important expression when it comes to UJT triggering of the SCR. So what will be the frequency? 1 upon RC ln 1 by 1 minus eta. What is eta? Eta is equal to RB1 over RB1 plus RB2. So let me summarize what we covered in this lecture. We first saw a resistance firing circuit, which is the most economical type of firing circuit, but the problem is firing angle is always less than equal to 90 degree. What was firing angle? It was the delay in the firing after a SCR becomes forward biased. Then we saw RC triggering circuit, which removed this limitation that alpha can be greater than or equal to 90 degree. That is how it did that. It shifted the capacitor voltage by an angle 90 minus phi so that the firing angle can be greater than 90 degree. Then we saw UJT triggering circuit. In UJT, we saw what is the working of the UJT. Then we saw that UJT can be used to create a relaxation oscillator with time period RC ln 1 upon 1 minus eta, where eta is the RB2 over RB1 over RB2 plus RB1. That is the intrinsic standoff ratio. So that way also we can trigger the SCR. So these are some of the most standard circuits that are used for SCR triggering. So in the next lecture what we will do is we will see how to protect the SCR from different abnormal conditions so that it does not get damaged. That we will see in the next lecture. Hi guys, in the last lecture we saw the firing circuits of the SCR. In firing circuits, we first saw resistance firing circuit. which was the most economical type of firing circuit, but the alpha could only lie between 0 and 90. Then we saw the RC firing circuit, which removed this limitation so that alpha can be greater than 90. Then we saw the UJT firing circuit. UJT is the unijunction transistor, which is implemented as a relaxation oscillator to provide gate pulses to the SCR. The time period of the pulse was RC ln 1 upon 1 minus eta. This was the time period of the oscillations by the UJT. In this lecture, we will see what kind of protection schemes do we use for the protection of SCR. The first is the overcurrent type of protection. Now, as we study in the power system, the purpose of fuse is to melt down whenever the heat produced in the switch is greater than the thermal limit. Or in case of overcurrent, after a certain time delay, the fuse is blown. So we connect a fuse in series with the circuit in order to protect it against overcurrent. The other protection scheme against overcurrent is this crowbar thyristor. Now what is a crowbar circuit? A crowbar circuit is a circuit which will short circuit the supply in case of overcurrent. So here what happens with the crowbar thyristor? If this current I, if this I is high, then what happens is voltage across the resistance is also high. If voltage across this resistance is also high, then this gate trigger circuit will trigger the SCR. So SCR is triggered. If this SCR is triggered, then this terminal is short circuited so that no power goes into the power converter and converter is protected. Okay. So that is why it is called as crowbar thyristor, because crowbar circuit short circuits the supply in the event of a overcurrent. So we can protect the SCR by means of fuse, and we can protect the power converter by means of a crowbar thyristor. So what will happen is, first this crowbar thyristor will operate and short circuit the supply. So the entire overcurrent will flow through the crowbar thyristor. But before this thyristor gets damaged, this fuse will be blown. Hence this thyristor will also be protected. Actually, the special thing about the SCR is high short time current rating, that is, or high surge current rating. Means a very high current can flow through the SCR if it flows for a short duration. That is why it is used for protection against the overcurrent, because it can handle high current. The next type of protection is the over voltage protection. Now, what we do for over voltage, whenever we have a SCR, we will connect a variable resistance through it, which is called as varistor. Now varistor is nothing but it is a metal oxide which is a non-linear type of resistor. If it is a non-linear type of resistor, the IV characteristics are like this. Now the slope of the characteristics determine the resistances. So if you see, the slope of the characteristic goes on decreasing. So as the voltage or the current increases, the resistance reduces. With increase in voltage, resistance reduces. If resistance reduces, then this resistance will reduce, and hence the voltage drop across the SCR will also reduce. So VAK reduces. If VAK reduces, then we have protected the SCR against the over voltages. The next protection comes is dV by dt protection. Now what is dV by dt protection? As I told you about the dV by dt triggering, what I told you is, whenever junction capacitance into dV by dt is greater than latching current, or let us say greater than or equal to, then SCR is triggered. Though you do not intend it to trigger, but it will trigger. It is called as false triggering. Okay. So what is the critical value of dV by dt? It is equal to latching current by junction capacitance. This is the capacitance of actually the junction J2. Now how to protect against dV by dt? To protect against dV by dt, we use a RC snubber circuit. What is a RC snubber circuit? It is a series RC circuit connected in parallel to the SCR. Here, capacitor will limit the dV by dt, and when the capacitor will get charged, actually dV by dt will now become Cj plus C. Okay. So actually the equivalent capacitance we have increased, so dV by dt rating we have reduced, or we have reduced the actual rate of dV by dt. So the capacitor will get charged. But when the thyristor will be on, this capacitor will need to discharge. If capacitor needs to discharge, it will discharge through this resistance R. So this R will limit discharging current, because discharging current will be V by R e raised power minus t by tau. So this R is used to limit the discharging current. Otherwise, in the on state, SCR may get damaged if high currents flows through the SCR. So remember, whenever the SCR is off, we apply a high dV by dt. That dV by dt rate is reduced by a capacitor connected across the SCR. And when SCR turns on, this capacitor will discharge itself through the resistance R and the SCR. So that is how we protect against the dV by dt rating. Next is the di by dt protection. What is meant by di by dt? What happens is, if di by dt rating is high, that is, the current rises at a faster rate. If the current rises at a faster rate, then what happens is, the charge carriers may not be spreading through that rate. If charge carriers are not spreading at a high rate and the current is continuously increasing, then the current will be constricted into a small region. If high current flows through the small region, then a lot of heat will be produced in that small region, which is called as hot spot. So hot spots will be formed within the device, which can damage the device. So we need that a current must also spread through the area at a high rate, at the rate at which the current is rising. So remember, here we are comparing two rate, dia by dt and rate of spread of charge carriers throughout the device. Okay. Now one of the method to protect against the di by dt is connecting a inductor. So if you connect an inductor in series with the SCR, then this inductor will limit the value of di by dt. So that is one of the method. The other method is to improve the di by dt rating is by changing the structure of the device. This type of device is called as side gated SCR, because here the gate is at one side of the device. Now when the charge carriers are injected, they will go into the N plus emitter. So this is the initial conduction area, because this is a cylindrical device. So cross sectional area will be circular. So the point at which charge carriers are injected will become conducting, and this will be the conduction area. That means the anode current will flow through this area. If high anode current flows through this area is very small, it will cause hot spot formation. So what we do is, we take the gate terminal in between the two cathode region. We have divided the cathode region into two parts, and in the center we have applied the gate. This is called as center gated SCR. So what happens when charge carriers are injected into the cathode junction? The charge carriers will follow a circular disc pattern. So here initial conduction area is much higher as compared to the side gated SCR. That is why if initial conduction area is high, current density will be low and it will not cause the hot spot formation. That is why center gated SCR is more preferred as compared to the side gated SCR. Okay, that is by structural modification we can improve the di by dt rating. The other method is by increasing the gate current. Either increase gate current or dig by dt, because the more the charge carriers you inject through the gate, the more this conduction area will spread. Okay, because wherever these charge carriers will reach, that area will become conducting. So normally if you are injecting 100 charges instead of 50 charges, then they will spread at a faster rate and initial conduction area will increase. So that is one of the method of increasing the di by dt rating. And the last method is by distributing this cathode and gate uniformly. That is called as interdigitated. But remember, whatever structural modifications we are doing, though it is improving the di by dt rating, at the same time it is increasing the cost. So it is P, then N plus, then P, then N plus, then P, then N plus, like in a matrix form, then P, N plus P. This way the gate and the cathode will be interdigitated, so that whenever we are injecting charges through the gate, they will be more uniformly spread in the cathode region, and hence they will be easier to conduct the current. Next type of protection is called as thermal protection. So whenever current flows through the device, it will cause I square R losses, which will cause heating. This heat needs to be dissipated by means of heat sink. Okay, what is a heat sink? It is a metallic junction on which our device is mounted so that it can radiate the heat to the atmosphere. So it follows the process of radiation. Okay, now this is the device that we are showing. P average is the average power loss. Then there is some thermal resistance between the junction and the casing. C refers to case, that is the outer covering of the device. Then S refers to the theta Cs refers to the sink temperature, that is the heat sink. S refers to sink. So theta Cs is the thermal resistance between the case and the sink. Then A refers to the atmosphere or ambient. So theta Sa is the thermal resistance between the sink and the ambient. So now when heat will flow like this. So all these thermal resistances will lie in the series. That means if we convert this thermal circuit into the electrical circuit, all the thermal resistances will be connected in series. The unit of the thermal resistance is degree centigrade per watt. So if we see the unit of resistance, it is volt upon current. So this temperature difference acts as the voltage difference, and this power acts as the current. So that is why the power will flow in this. This is the current source, and the potential difference will be the temperature difference. So Tg minus Ta will be average power loss, theta Jc, theta Cs, theta Sa. That is the thermal resistance from the junction to the ambient or the atmosphere. That is the total thermal resistance. And remember, current rating will be directly proportional to square root of the power rating of the SCR. Sorry, it will be the power loss in the SCR, because power loss is I square R. So remember, this is the average power loss. Okay, so what happens is, the higher the thermal resistance, then this average power loss will reduce. Or we can say the lower the thermal resistance, then the temperature difference would be low for even a higher power loss. So power loss rating will improve, as well as the current rating will improve. For the same temperature difference, if your thermal resistance is low, then power loss will be high. So the current rating will also be high. So to improve the current rating, we need to have a low thermal resistance. Low thermal resistance implies that heat can easily flow from the junction to the ambient, and heat can easily be dissipated. That is the significance of the low thermal resistance. At the last, we protect the gate of the SCR. What is needed in the gate protection is, we need to connect a resistance in series with the gate. Why? Because this resistance will limit the gate current. As I told you, gate current should always lie between the minimum and the maximum limit. This we saw during the triggering. So to limit the gate current within the maximum current, we will use a resistance in the series. Other than that, to prevent unwanted triggering or to prevent the noise from triggering the SCR, we connect a RC filter at the gate. Okay. Otherwise, what happens if there is a noise signal, then it can cause the gate current to be induced, which will cause the triggering of SCR. So we have to use a RC filter. This will be connected here. So these are the two methods to protect the gate from unwanted triggering as well as to limit the gate current within the maximum value. The third method is this Zener diode. This will limit the gate voltage less than the gate maximum. Because when the Zener diode will be on, it will clamp the gate voltage to a fixed value. So these three methods are used to keep gate current within a nominal value, gate voltage within a fixed value, and also prevent unwanted triggering of SCR due to noise. So this figure illustrates all the protection schemes that we have studied so far. This is the fuse for overcurrent protection. This is the inductor for di by dt protection. This is the heat sink for thermal protection. This is the RC snubber circuit for dV by dt protection. This is a varistor for over voltage type of protection. And rest are the protection scheme for the gate protection. So this is how an entire thyristor looks like, or an entire SCR looks like, with all the protection schemes implemented. Now let us see what are the gate characteristics of the SCR. Now what is meant by gate characteristic? It means the graph between VG and IG. Now gate characteristics also have certain limitation, like gate voltage can have a certain maximum value. Similarly, gate current also has a maximum limit, and in between that we have the power limit, where PG is equal to VG into IG. That is, the gate power should not go beyond this value, hence the curve looks like a hyperbola. This line A to D represents a load line, that is, gate voltage reduces as gate current increases, because VG is equal to actually EG minus IG into RS, that is the series resistance. EG is the voltage applied at the gate. So it will reduce as the gate current increases, and when it intersects with the gate characteristics, we will get the operating point like S, S2 and S1. Now we have to make sure that these operating points lie within these limits. They do not go outside these limits. Okay. So here minimum limits also are shown, VG min and IG min. So remember how to determine the operating gate characteristic. We will plot the gate characteristic, that is a curve between VG and IG, and also we will plot the characteristics of the load line, and whenever they intersect we will get the operating point. Now we have to make sure that this operating point lies within the safe region so that device operation is safe. Now what is the circuit that we will use to trigger the SCR? We have applied a voltage source in series with a resistance, and this is a shunt resistance which will be used to create the voltage VG. Now by KVL I can say ES minus IG into RS is equal to VG, where RS is the series resistance. This will be the voltage VG. Now power dissipated in the gate is PG is equal to VG into IG. Also the gate characteristic will have a certain slope. Slope will be VG upon IG. Okay. Now if we are given the slope and we are also given the power dissipation, then we can determine this value of RS. How? You will solve these two equations to determine VG and IG. Once I know VG and IG, I know what is the series resistance required in order for the SCR triggering. Okay. So that is how we trigger the SCR. Then what is the purpose of this R1? It provides an easy path to the flow of leakage current. If there is any leakage current between the SCR terminal, that is the gate cathode current, it will provide a low resistance path to the flow of such current. Okay. So remember, whenever we talk of the gate cathode characteristic, we know the maximum power dissipation as well as we know the slope of the gate cathode characteristic. And from that we can derive the value of gate voltage and gate current, which will give us a value of the series resistance required for triggering the SCR. So let us summarize what we covered in this lecture. We first saw the overcurrent protection. In that we saw we can use a fuse or a crowbar thyristor. Then we saw over voltage protection, which is done by connecting a varistor, which is a metal oxide resistance, across the SCR. Then we saw dV by dt protection by means of a RC snubber. Then we saw di by dt protection by means of inductor. By means of structural changes, that is a center gated thyristor or interdigitated structure or high Ig or high dig by dt. Then we saw thermal protection by means of heat sink. Then we saw gate protection by means of Zener diode, series resistance and the RC filter. Zener diode protects against the over voltages at the gate terminal. RS protects against overcurrent at the gate terminal. RC filter avoids the noise. Then we saw the gate characteristics of SCR. In the gate characteristics, we plot the curve between Vg and Ig. If we plot between Vg and Ig, then we can determine average power dissipation, as well as from the load line we can determine the Ig and Vg. From there we can determine the series resistance Rs. And we are always given the slope of the characteristic, that is Vg by Ig. So in the next lecture we will see how to connect the SCRs in series and parallel in order to increase their rating, and what are the issues when we operate two SCRs in series or in parallel connection. So that we will cover in the next lecture. Hi guys, in the last lecture we saw about the protection of SCR. In which we saw overcurrent protection, which we did by means of fuse and the crowbar SCR. Then we saw over voltage protection, which we did by means of varistor. Then we did dV by dt protection, which we did by means of RC snubber. Then we did di by dt protection, which can be done by inductor, higher gate current or structural changes, in which we saw center gated SCR has more di by dt rating as compared to the side gated SCR. And also we saw interdigitated structure, in which gate and cathode are intermixed so that the di by dt rating is high. Then we saw thermal protection, which is done by means of heat sink. Then we saw gate protection, which is done by means of Zener diode, series resistance and RC filter. And last we saw thyristor gate characteristics, in which we saw that Vg into Ij is the average power and Vg by Ig is the slope of characteristics. This helps us in determining the series resistance, which is Eg minus Vg is equal to Ig into Rs. So in this lecture what we will do is we will see how to connect SCRs in series and parallel and what are the problems related to each configuration. Now first of all let us consider the series connection. Now in series connection what we do is we connect the SCR in a string or in a series. Why we do that? Because in series the voltages get added up but current remains same. So it will increase the voltage rating. Okay, so voltage rating increases in terms of series configuration. So that is one of the motivations of the series connected SCR. But the thing is, they may or may not be able to share the voltage corresponding to their rated voltage. That is, suppose two SCRs are there, then it is, let us say, 5 kV, it is 10 kV. But suppose if we apply only 10 kV voltage, then they are supporting 10 kilovolt voltage, but their capacity is 15 kV. So this will be 66.67%. So that is called as your string efficiency. String efficiency means what is the voltage supported by the total string of the SCRs divided by sum of the ratings of the individual SCR. So eta is voltage across string divided by sum of the ratings, or we can say number of SCR into voltage rating of each SCR. Okay, that will give us a string efficiency. Now what does the string efficiency indicate? It indicates how efficiently are you using a string of series connected SCR. That is, if this can suppose 20 kilovolt, how efficiently are you utilizing their capability for the series connection. Similarly, we define derating factor. It is just the opposite of string efficiency. So derating factor is actually 1 minus eta. Higher the derating factor, lesser is the efficiency. Derating indicates how much the rating has reduced while series connection, because if the rating had been maintained then they would be supporting 15 kV, but now they are only supporting 10 kV. That means how much the rating of the series connection has reduced, that is called as the derating factor. So now these are the two terms that are associated with the series connection of the SCR, where string efficiency bears the same formula as we study in case of insulators in power system. In overhead insulator, we determine the string efficiency of the series connected insulators in a similar manner as to the series connected SCR. Now Now, there are certain problems when we consider the series connection. What are those problems? First is the unequal sharing of voltage during the forward blocking characteristics. In forward blocking mode, what happens? SCR is off. So which region of the characteristics lies in the forward blocking mode? This region. Okay. This is the region that lies in the forward blocking mode, and the characteristics from here, this is the forward conduction mode. Now when they are forward blocking, ideally they must be blocking the equal voltage so that none of the SCR is overstressed and none of the SCR is understressed. Overstress means bearing a higher voltage as compared to its rating. Understress means having a voltage much less than its rating. Now how can you say that it has an unequal sharing of voltage? The reason for unequal sharing of voltage is difference in forward blocking characteristics. Now if you see on the graph here, I have shown two different characteristics of the two different SCR. Now if we keep current same like this, since they are in series, current will be same. We get two values of voltages, that is V2 and V1, where V2 is less than V1. Now due to this, one switch may be overloaded or it may have over voltage which can damage the switch or which can damage the SCR. Hence it is always undesirable to have different voltages across the SCR, otherwise one gets overloaded and other is underutilized. Now what is the remedy? What we do to remove this unequal sharing of voltages? We connect resistances across the SCR. Here we have connected resistance R and the resistance R here. Suppose it has a voltage V1, the current through this will be V1 by R. If it has a voltage V2, current will be V2 by R. Now, what we can say by KCL, V1 by R plus IB1 should be equal to V2 by R plus IB2. That means V1 minus V2 is equal to R into IB2 minus IB1. Okay, that will be the difference in the voltage of the two SCR. And the other relation will be V1 plus V2 should be equal to Vs. Okay. Now, since they are connected in series, how I am assuming current is different? Because due to introduction of this resistor, current may or may not be equal in the two SCR. Because now they are no longer connected in series. Is it fine? So by solving these equations, we can calculate V1 and V2. Now, if we connect multiple SCRs, we will have multiple resistances, one across each SCR. Okay. So these are n minus 1 SCRs with leakage current IBMX. This is one SCR with leakage current IBA min. So there is one SCR having the minimum leakage current and other SCRs have the maximum leakage current IB max. So change in the leakage current will be IB max minus IB min. Now the resistance R should be chosen something like this. R should be greater than or equal to N into VBM divided by N minus 1 delta IB. Okay, where N is the number of SCR. Okay, so this should be the value of resistance, where VBM is the maximum blocking voltage. Okay, so these are the terms that are associated with the series connection of the SCR, and this circuit where we are connecting one resistance across the each SCR is called as static equalizing circuit. Okay, because it is under steady state that they are sharing unequal amount of voltage. It is not the transient state. The other problem that is associated with the series connected SCR is the unequal reverse recovery time. Now what is the problem with the unequal reverse recovery time? So first let us understand what is meant by reverse recovery time. It is the time required by the device to remove the charge carriers or the excess stored charge carriers from the junctions in the device. Now, if these charge carriers are not removed from the device, what is the danger? That they will act as the gate current and can cause false triggering of the SCR. That is, we will lose control over the SCR turn on due to this stored charges. So, if the reverse recovery time is not equal, then what will happen? One SCR will be able to recover faster than the other SCR. What is meant by recovering? That means now it will be able to block the reverse voltage after when it is reverse biased. Okay. So, it has to regain its blocking capability in order to recover from the reverse characteristics. Now, if they have different times, then one will recover faster, other will recover slower. The one that recovers faster will now become non-conducting. Once it recovers, it enters blocking mode. That means its current becomes 0 or it becomes open circuited. Okay. So, reverse recovery also indicates that the thyristor will now become open circuited. But the one that is recovering later than this is still conducting. That means it is still acting as a short circuit. That means out of the two switches, only one switch is open, other is short. So in series connection, one is open, other is short, due to which the entire voltage V will appear across one switch. And if this V is greater than reverse breakdown voltage, then this junction will break down. That is undesirable. So let me explain you once what is happening again is, there are two thyristors having different reverse recovery characteristics. So one thyristor will recover faster and will support the entire blocking voltage until the other thyristor recovers, due to which it can also break down or can get damaged. So the shaded portion here in the graph indicates the change or the difference in the stored charge carriers between the two SCR. Okay. Area indicates the stored charge carrier. So difference in the area or area between the curve indicates the difference in the stored charge carriers between the two types of SCR. Here, to avoid this kind of situation or unequal reverse recovery time, we connect a RC circuit across the SCR. Now what happens with the RC circuit? During the charging time, the voltage will be defined by this capacitors, and their recovery rate will also be determined by the capacitors, because C dV by dt will be equal to capacitor current. So the rate of voltage change will be determined by the capacitor. And when the capacitor will discharge during the turn on of the SCR, then it will discharge through this resistance R. So this resistance in series with capacitor is included to limit the discharging current. Okay. Because the discharging current will be V by R e raised power or 1 minus e raised power minus t by tau. Okay. So that will be the discharging current. To limit it to a value V by R, we have to include a resistance, that is R. And this resistance here forms the part of static equalizing circuit, which tends to make the equal sharing of voltage in the series connection. So remember, in series connection we have two types of circuit. One is the static equalizing circuit, other is the dynamic equalizing circuit. And the role of static equalizing circuit is to ensure that the voltage is shared equally between the two devices. And in dynamic equalizing circuit, we mean to make sure that the both devices recover together. Now this capacitance C is given by n minus 1, that is n is the number of SCRs, into delta QR. Delta QR is the difference in the reverse recovery charge. N into VBM, that is the maximum blocking voltage, minus Vs. This will be the capacitance in the series connected SCR or in the dynamic equalizing circuit. Okay. So here Vs indicates the supply voltage. So this is all about your series connected SCR. Now let us move on to the parallel connection. Now why do we connect in parallel? In parallel, what happens is the current will get divided between the different devices. So if current gets divided, then effectively we can push more current. So rated current increases. Suppose initially each device can carry I, then the two devices in parallel can carry a total current of 2I. Hence the rated current increases in case of parallel connection. So SCRs will be connected in series in order to increase the voltage rating, in parallel in order to increase the current rating. Now what is the problem with the parallel connection? In parallel connection we will talk about the forward conduction mode. In forward conduction mode, due to difference in the forward conduction characteristics, both SCRs will share unequal amount of current for same voltage. In parallel connection, what is the essential condition? That V1 is equal to V2. Now even if you keep the voltage same, their currents are different. So I1 is not equal to I2, which is undesirable. We need to ensure that the thyristors share equal current, otherwise one will get overloaded and can get damaged. So to do that, what we do is we take a current equalizing circuit. Okay, what we do in this connection is these are the two SCRs. We connect an inductor between these two SCR. Okay, like this. Now what happens? In accordance to the Lenz's law, always inductor opposes the change in current. So now if this is I1, this is I2. Now if there is a difference between these two currents, then there is a net inductor current or there is a net inductor voltage. I1 is not equal to I2, then voltage will be induced like VL1 and this VL2, which will oppose this difference in the current and will try to make both the currents equal. So that current in the inductor is 0 and hence the voltage in the inductor is also 0. Because whatever is the induced EMF will try to oppose the cause of induction and will try to make the currents in the SCR equal. Here the load current will be I1 plus I2 constant. So if any of these currents changes, then EMF will be induced in the inductor which will oppose the change in current. That means suppose if I1 increases, then L di1 by dt will be greater than 0, due to which voltage across this SCR decreases. Because suppose this is supply voltage, then voltage across SCR V1 is supply voltage minus VL1. So if I1 current increases, then this VL1 is greater than 0, due to which V1 reduces, due to which current reduces. Similarly, if I2 reduces, then L di2 by dt will be less than 0. Because if I1 increases, I2 must decrease in order to make the sum constant. Now V2 will be Vs minus VL2 and this is equal to VL2, which is negative, so it will be greater than Vs. So thyristor 2 voltage increases, which will try to increase the current. So if I1 increases and I2 decreases, the effect of inductor is to oppose the change and try to bring the currents to an equal value. And also whenever there is a temperature difference between the SCRs, then also current sharing may be unequal because temperature affects the characteristics of the SCR. If temperature is different at different devices, then their characteristics will be different, due to which current will be shared unequally. So we use a symmetrical heatsink that is symmetrical across all the devices connected in a circuit, or we can say that all the SCRs will be mounted on the same heatsink in order to have same temperature of each device. Because remember, temperature difference is always undesirable as it alters the characteristics of any device. So let me summarize what we covered in this lecture. We first saw series connection, in which we saw efficiency. In efficiency, what we saw is voltage across string over number of SCR into voltage across each SCR. Okay, then we saw derating factor which was 1 minus eta. Then we saw problem with the series connection. What was the problem? Unequal voltage sharing due to difference in the forward blocking characteristics and unequal reverse recovery time, which led to unequal sharing of the voltage in the reverse blocking mode, due to which one thyristor may have to support the entire reverse voltage and can get damaged in the process. Then we saw parallel connection. Now what was the problem in the parallel connection? Unequal current sharing due to difference in forward conduction characteristics and unequal current sharing due to temperature difference. So to avoid this, we use an inductor, and to avoid unequal current sharing due to temperature, we use a symmetrical heat sink. Okay, so no need to go in much depth in the series and the parallel connected SCRs. No need to memorize the formulas for the resistances and the capacitances. Just you have to remember the basic concept. Okay, so in the next lecture what we will do is we will see problems based on SCR. What is each type of problem that can be framed from this topic, because there is a limited set of problems that can be framed from the SCR. Hi guys, up to now we have covered the two power semiconductor devices, that is a power diode and an SCR. So in this lecture what we'll do is we'll look at some of the problems that have appeared in GATE examination from the topic of SCR. So let us get started with our first problem. It is saying that the figure shows two thyristors each rated 500 ampere sharing a load current. Now current through the thyristor Y is 120 ampere. Then what is the current through the thyristor X? Now, since they are operating in parallel, their voltages must be same. Since no voltage is given, voltage drop is given in the thyristor, that means voltage of X is equal to voltage of Y is 0. That means the entire voltage drop is across this resistance. So if you equate the voltage drops, 120 into 0.05 Ix into 0.06. So Ix will come out to be 100 ampere. This will be the current shared by the thyristor X. That means the current shared by the two thyristors will depend on the series resistance of each thyristor. It does not depend on the any property of the thyristor itself. Why? Because the voltage drop across the thyristor is given as 0. In our next problem, it is saying the triggering circuit of a SCR is shown in the figure. The thyristor requires a gate current of 10 mA for guaranteed turn on. We need to find the value of resistance R for turn on of a SCR. Okay. So now we need to know what is the value of resistance for reliable turn on. This voltage varies between 8 to 16 volt. That means if a thyristor can turn on for 8 volt, then it will definitely turn on for 16 volt, because if Ij is greater than Ig min, then SCR turns on. That means if it turns on for 8 volt, then guaranteed turn on for V greater than 8 volt. Okay, so that means we have to check the condition at 8 volt. Now it is saying that it requires a gate current of 10 milliampere. If it is getting a gate current of 10 milliampere at 8 volt, then it will get the gate current higher than this for any value of other voltage. So R will be 8 minus V GK upon 10 milliampere. GK means the gate cathode voltage. Now gate cathode voltage is not given, so I will assume it to be 0. So resistance will be 0.8 kilo ohm, or we can say 800 ohm. So if you take this value of resistance, then it will be causing reliable triggering, because now suppose you take 16 volt. Now 16 by 800 will be how much? It will be 20 milliampere, which is greater than 10 milliampere. So the thyristor will turn on. That means in the question it is given to me the minimum gate current required for turning on a SCR. So you have to take the minimum voltage in order to derive a resistance which is guaranteeing the turn on of a SCR. In the next problem, it is asking about the minimum gate pulse width required. Now minimum gate pulse width requirement is related to the latching current, because as I told you, latching current is related to turn on process of a SCR. Now how to deal with this kind of problems is, you will assume that SCR is on. Once you have assumed that SCR is on, then what you will do is, you will find the time at which current is equal to latching current. So first we need a general equation for current. It will be V by R 1 minus e raised power minus t by tau. That is the equation for a charging RL circuit. Okay. So now what you will do is, you will find the time at which this current will become equal to the latching current. So latching current is 100 milliampere, voltage is 100 volt by 20 minus t by tau, where tau will be equal to L by R, that is 0.1 by 20, 0.005. Break. Resuming the lecture. So this will come out to be 5. So 20 into 10 raised power minus 3 is equal to 1 minus e raised power minus t by 0.005. So now if we simplify this, 1 minus 0.02, that is 0.98, is e raised power minus t by 0.005. So t will be into ln 0.98. This will come out to be almost 101 microsecond. That means you have to apply the gate pulse for a time greater than 101 microsecond for reliable triggering of the SCR. Otherwise, if you apply a gate pulse width of less than this time period, then the SCR will fail to turn on. Okay? Before turning on itself, it will turn off. In our next problem, it is saying we have been given a turn on time. That means minimum pulse width is equal to 5 microsecond. You have to apply a pulse width greater than or equal to the turn on time of the SCR. So minimum width will be 5 microsecond. Latching current will be 50 milliampere. Holding current is 40 milliampere. Since turn on process is related to latching, so we will be interested in the latching current. Now it is triggered by a short duration pulse and is used in the circuit shown in the figure. The minimum pulse width required to turn on the SCR. Okay, here it is asking the minimum pulse width. So let us determine the minimum pulse width. Again we will assume SCR is on. Now when SCR is on, SCR will contain two currents. One is a current in this branch, other in this branch. That is I1 plus I2 is equal to ISCR. Now when ISCR is equal to latching current, it is equal to I1 plus I2. Now I1 is the current in a RL circuit, 50 milliampere, that is V by R 100 by 20 plus 100 by 5, that is 20 milliampere. So if we take it to the left hand side, 50 minus 20 will give me 30 milliampere, which will be equal to 5 1 minus e raised power minus t by tau. 1 minus 6 milliampere, that is 0.006. Now it will be 0.994. T is equal to tau. Tau is 0.5 by 20 ln 0.994 with a minus sign. So this will come out to be how much? This will come out to be 150.45 microsecond. Okay. So this will be the minimum pulse width required. It is greater than the turn on time that is given to me in the problem. So we will have to consider this value. If turn on time would have been greater, then that means we have to take into consideration the turn on time of the SCR. You cannot apply a pulse width less than the turn on time of the SCR. Since it is already much higher, it won't create any problems. In our next problem, it is saying for a thyristor, maximum junction temperature is 125 degrees centigrade. The thermal resistances for thyristor sink combination are theta JC, that is junction to case, theta CS, that is case to sink. Now for a heat sink temperature of 70 degrees centigrade, compute the average power loss in the thyristor sink combination. In case the heat is brought down to 60 degrees centigrade by forced cooling, we need to find the percentage increase in the device rating. Now first of all, what do we need to understand is that heat generated depends on power loss in the device. But what is the rating that it is asking in the question? The thing is, power loss is never the rating, but power loss is always proportional to I square, where I is the current rating. So it is asking about the change in the current rating if you decrease the temperature of the ambient to 60 degrees centigrade, or if you decrease the temperature of the heat sink to 60 degrees centigrade by forced cooling. So let me consider first initial case. What will be the theta JS, that is junction to sink, theta JC plus theta CS. They will be connected in series, 0.24 degree centigrade per watt. Now as I told you, Tj minus Ts, that is the voltage difference or the temperature difference, theta Js, that is the thermal resistance, into in place of current we will have power. Now if you take Ts as 70 degree centigrade initially, this will be 0.24 into P1. From here, P1 will come out to be 229.167 watt. Now, suppose we bring down the heat to 60 degrees centigrade, then what will be the new power dissipation. It will be 125 minus 60.24 into P2. So this P2 will come out to be 270.834 watt. Now as I told you, power is proportional to I square. That means current is proportional to square root of power. That means percentage increase in current rating will be same as percentage increase in square root of power rating or losses in the device. 270.834 minus 229.167 into 100%. So this will come out to be 8.71%. So that is the percentage increase in the current rating of the device. So always remember this one point, that the losses are never counted as the rating. Hence in the case of thermal resistance, whatever we derive is losses and they do not consider as rating. We have to determine the current rating using the losses. In our next problem, it is saying the gate cathode characteristics have a straight line slope of 140 for trigger source voltage of 20 and allowable gate power dissipation of 0.5 watt. We need to find the gate source resistance. So this is a standard problem based on the gate characteristics of a thyristor. Here we need to find the series resistance in the gate. Now slope is given, that means Vg by Ig is 140, or what I can say is Vg is equal to 140 Ig. Now it is saying the trigger source voltage, that is Eg. Eg is 20 volt and P average is 0.5 watt, which is equal to Vg into Ig. So 140 Ig square is equal to 0.5 watt. That means Ig will come out to be 0.0597 ampere, due to which Vg will come out to be 140 into this, that is 8.367 volt. So now we have Vg as well as Ig. Vg is actually Eg minus Ig Rs. So Rs will be Eg minus Vg by Ig. So this Rs will come out to be 194.8 ohms. Okay, so this will be the series resistance connected in the gate circuit for the case of reliable triggering. Okay, or for the case of gate cathode characteristics that are given in the problem, so that the device is within the safe limits and it is turned on. In our next problem, it is saying a 1:1 pulse transformer is used to trigger the SCR in the adjacent figure. Okay. Now SCR is rated at 1.5 kV, 250 ampere, latching current 250 milliampere, holding current 150 milliampere. Ig max 150, IL 250. So this value is repeated, cancel it. Ig min 100 milliampere. The SCR is connected to inductive load where L is 150 millihenry. So this is 150 millihenry. Connected in series with a small resistance, that is 1 ohm, and the supply voltage is 200 volt DC. Now forward drop of all transistor diodes and gate cathode junction during on state are 1 volt. We need to find the value of resistance. Okay. Now to determine the value of resistance, we need to ensure that Ij is always greater than Ij min. Okay, because if it is greater than Ig min, then it will cause reliable triggering. Now it is saying the forward drops of all transistor diode is 1 volt. Since the drop of this transistor is 1 volt, what is the voltage across the potential transformer pulse transformer winding? It is 10 minus 1, that is 9 volt. Since pulse transformer is 1:1, on the secondary side also we will have 9 volt. Now this diode will have a voltage drop of 1 volt. That means voltage, let me call it as point A, will be 9 minus 1, that is 8 volt. And voltage of the gate cathode junction, voltage of gate cathode junction is 1 volt again. That means VB will be 1 volt. This is the point B. So what is the voltage across the resistance? It is VAB, that is 8 minus 1, that is equal to 7 volt. Now I know the voltage across the resistance is 7 volt. I know that the current can vary between 100 milliampere to 150 milliampere. Then we need to determine the value of resistance. So there will be two values, R1, that is 7 by 150 milliampere, and R2, that is 7 by 100 milliampere. 7 by 150 will come out to be how much? 46.7 ohm. And this value will come out to be 70 ohm. Now the problem arises, which value should we consider? We will consider the minimum value because minimum resistance implies higher current. This implies higher current. If current is higher, then it is for the case of reliable triggering. Is it fine? So that is why we have to consider the higher value of current or the lower value of resistance. So that will give me the resistance for the reliable triggering. In the next part of the same problem, it is asking the volt second rating of pulse transformer. Now what is meant by volt second rating? Volt second rating means voltage of the pulse transformer, and the time will come from minimum pulse width. So the product of these two will give me the volt second rating. That is, what is the voltage and for how much time does it exist? It should exist for a time greater than equal to minimum pulse width. Now what is the latching current? 250 milliampere. This will determine the minimum pulse width. Now minimum pulse width is always determined from the point of view of power circuit that is connected between the anode and the cathode terminal. Gate terminal has nothing to do with the minimum pulse width requirement. So in the anode to cathode, we have the voltage source of 200 volt, resistance of 1 ohm, inductance of 150 millihenry. Now the current in this circuit will be 200 by R 1 minus e raised power minus t by tau. This should be equal to 250 milliampere. Now this will be 200. 1 minus e raised power minus t by tau will be R by L, that is 0.15. Sorry, L by R, that is 0.15. It is equal to 250 milliampere. So if we simplify this, it will come out to be 1.25 into 10 raised power minus 3, that is 0.00125 1 minus e raised power minus t by tau. So that is time will be 0.99875 into log of this into minus sign into tau. So this comes out to be 187.6 microsecond. Now what was the voltage applied at the potential transformer? So the supply voltage at potential pulse transformer was 10 volt. So what is the volt second rating? That is 10 into 187.6 1876 volt microsecond, or we can say 2000 volt microsecond. Why I am saying 2000? Because in the options are like this, 2220. So the most appropriate one will be 2000 volt microsecond. Now do not confuse that the voltage across the potential transformer is 9 volt. Why I am considering 10 volt? Because the rating of the pulse transformer will be 10 volt, because it must be equal to supply voltage, that is due to the intrinsic voltage drop of the transistor that we are getting 9 volt. But you have to buy a pulse transformer corresponding to a rating of 10 volt, so that it can bear the supply voltage even if there is no drop across the transistor. Okay. So 9 volt is only due to the voltage drop. It is not the rating of the pulse transformer. In our next problem, it is saying an SCR has a half cycle surge current rating of 3000 ampere. We need to find the one cycle surge current rating. Now you have to understand about the surge current rating. Now what is meant by a surge? It means that it is a high value that exists only for a short duration. Like in power system, when you study surges, those are the transient condition in which high voltage is induced on a transmission line. Surge means high current, small time. So what is the energy of a surge? That is I square R into T. Now, the heat dissipated in a device should always be less than the thermal limit. So that means it should be equal to thermal limit upon some safety factor. Okay, whatever safety factor you are considering. So it means I rated square into T must be constant. So this is the concept about the surge current rating, that I square T remains same. Now the rating is 3000 ampere for half cycle. 3000 square half cycle is 1 by 100, because time period is 1 by 50, so half time period is 1 by 100. This is equal to full cycle surge current rating into, what is the period of full cycle? 50. So this I will come out to be 3000 by root 2. So how much is this value? 3000 by root 2. This comes out to be 2121.3 ampere. So if you see here, this rating is less than the half cycle surge current rating, because longer the time, smaller will be the current rating, because higher current should only exist for a short duration, otherwise it will produce more heat in the device, which will damage the device. So remember this concept about the surge current rating of SCR. In our last problem, it is saying the latching current of SCR is 4 milliampere. We need to find the minimum pulse width required. Here again we will assume SCR is on. Then it becomes an inductive circuit where L di by dt is 100 volt. So di by dt is 100 upon 0.1, that is 1000. That is gi is equal to 1000 dt. Now the current should go from 0 to IL in time 0 to T min. That means 1000 into T min is equal to 4 milliampere. So minimum pulse width is actually 4 microsecond. So if you apply a pulse width more than this, then the thyristor will turn on. So let us summarize what kind of problems can be framed from the topic SCR. One problem is IL and minimum pulse width. Other is the surge current rating of the SCR, which means I square T is constant. Then next is your based on the gate characteristics. Next is your parallel operation. Then thermal protection, which is related to thermal resistances. And what other problem can be framed? That is turn on or triggering circuit. So following kind of problems can be framed. So it is a very limited set of problems that can be framed from the topic SCR. Over the years, no problem out of this has been seen. Otherwise, one or two theory questions can be framed, but that we have covered in the lecture, so it would be easy for you to crack those sort of problems. In the next lecture, what we'll see is, we'll see some other devices that are used in the as power semiconductor devices from the thyristor family. Hi guys, up to now we have looked at one device from the thyristor family, that is the silicon controlled rectifier or SCR. So what we looked at in SCR is, we looked at the basic device construction, that is it consists of 4 layer PN with P acting as a anode, N acting as a cathode and 1 P acting as a gate terminal. Then we saw the conduction modes. The different conduction modes that we saw were forward blocking mode, forward conduction mode, then reverse blocking mode. Then what we looked at is, we looked at the dynamic characteristics of SCR, in which we looked at the turn on time. We looked at turn off characteristics, in which we saw the reverse recovery and the device and the circuit turn off time. Then we looked at firing circuits and triggering method of the SCR, like dV by dt triggering, forward voltage triggering. Then we looked at protection methods of SCR, that is over voltage over current protection, dV by dt and di by dt protection. And last we saw the series and parallel operation. So what we'll do in this lecture is, we'll take a brief look at some of the other devices that are included in thyristor family and serve some special kind of purpose. So the first such device is gate turn off thyristor. It is also known as GTO. Okay. Now the special thing about the GTO in addition to SCR is, it can be turned off with a negative gate pulse. So like in SCR, it can be turned on by a positive gate pulse, but now it can also be turned off by a negative gate pulse. So that means turn on is plus Ig, then turn off is minus Ig. Now what is the benefit of this feature? The thing is, there are some applications where we will need to turn off the SCR, or we will need to turn off the switch. Now how to turn off an SCR? You have to turn off a SCR by reverse biasing it for a time more than the device turn off time. But if the supply is AC, then for the half cycle SCR will be forward biased, for other half cycle it will be reverse biased. But if the supply is DC, then it will only be either forward biased or reverse biased. That means if it is forward biased, it will stay forward biased for infinite duration if the supply is DC. So DC nature of the supply does not support commutation of the SCR, because it can never reverse bias the SCR. In such cases, we make use of commutation circuit to turn off the SCR, but only when the supply is DC, like in case of inverters and choppers. Okay, that means here the GTO will be a bit more beneficial, because the turn off procedure is simple. Just you have to apply a negative gate pulse. No need to use commutation circuit. Hence, with GTO, commutation circuits are eliminated from the power electronics converter. Now, the representation of a GTO looks something like this. Here we have a bidirectional arrow which indicates gate current can be positive as well as negative. Similarly, here we have a bidirectional arrow, and here we indicate a cross or a dash sign to indicate it is different from SCR or it is GTO. Okay, because we have to make a symbol something bit different from the SCR. Is it fine? Now let us look at the switching characteristics of a GTO. How does it turn on and turn off? Now when we apply gate current, once the gate current reaches 90% of its value, then the device will start to turn on. That is, its voltage will start to decrease and current will start to increase. So the difference in the time when the gate current reaches 90% and the anode current becomes 10% is delay time, as we studied in SCR. Delay time is the time between the point where gate current becomes 90% of the maximum value and anode current becomes 10% of the maximum value. Then this anode current will increase and the voltage will reduce. So 10% to 90% increase is indicated by rise time TR. Then 90% to 100% by spread time TS. So T on is actually TR plus TD plus TS. Same as that of SCR. But the interesting part is when you will have to turn it off. Once it is turned on, we can remove the gate current and we keep the gate current at a low value, which is called as back Porsche current. Okay. This is just to ensure that you are injecting sufficient number of charge carriers so that the device remains on. Okay. So it is a low value so that drive losses are less. Even if it is not completely zero, it should be low to reduce the losses or to increase the efficiency of the gate drive circuit. Now, if you have to turn it off, then you will apply a negative gate pulse. And once the negative gate pulse reaches its maximum value, then the device will begin to turn off. That is, the anode to cathode voltage will anode current will start decaying and anode to cathode voltage will start increasing. Now, this time, the time taken by the gate current to reach the maximum negative value is your TS, that is the storage time. Now, storage time is basically the time required to remove the stored charge carriers. Once you have removed the stored charge carriers, then only the anode current will begin to decay. And the rate at which it decays, that is, it goes from 90% to 10%, is called as fall time. And 10% to 0%, it decays very slowly or gradually, is called as TT, that is your tail time. So the turn off time is actually TS storage plus fall plus tail. Okay. So turn on time is delay plus rise plus spread, and then turn off is storage plus fall plus tail. And remember, during the tail time, current decays very slowly, which appears as a tail in the characteristics, and hence it is called as the tailing time of the GTO. Is it fine? Now we define as two terms. One is the turn on and the other is turn off gain. So what is turn on gain? It is the maximum anode current by maximum positive gate current. Similarly, turn off gain is maximum anode current which is turning off and the maximum negative gate pulse, because negative gate pulse will be used to turn off the GTO. Okay, so these two terms are defined with respect to the switching characteristics of a GTO. Now let us compare the performance of a SCR with a GTO. What are the essential difference between the two devices? So the first is that latching and holding current in GTO are less as compared to latching and holding in SCR. It is less than this current. Okay, that means the stored charge carriers in GTO are much less as compared to the SCR. Okay, because then only the latching current will be lesser and you will require a lesser pulse width to turn on the GTO. Now if you require lesser pulse width or you have lesser charges, then you can turn it off or turn it on at a faster rate. That means T on and T off in GTO is less than T on T off of SCR, because there is a less charge storage and lesser current is required to turn it on, so minimum pulse width requirement will also reduce. That means switching frequency increases. Okay. Next is on-state voltage drop and conduction losses. These are higher in case of GTO. Okay. Now why it is higher in GTO? Because whenever you have a higher switching frequency or the device operates faster, the losses will also increase, or we can say it has a higher on-state resistance. If it has a higher on-state resistance, then the voltage drop as well as power loss will be high. Next is, in case of GTO, though we haven't looked at the circuit or we haven't looked at the schematic of a GTO, how it is implemented in semiconductor terms, but you have to remember that it has multi-cathode structure. Multi-cathode structure means the cathode has been divided into multiple parts so that the charge carrier injection from the gate terminal is more. Okay, just like in case of center gated SCR. If more charges are getting injected in the GTO, the gate current is higher. Okay, if instead of one hole you are injecting two holes, then the current becomes twice. So gate current is high due to multi-cathode structure. Now if gate current is high, the gate losses is also high if the gate current is high. That means the efficiency should reduce for the case of GTO due to higher gate drive losses. But actually that is not the case, because as I told you, in case of GTO, due to the self turn off capability, that is it can be turned off by a negative gate pulse, we do not require any commutation circuit. So due to elimination of commutation circuit, the losses reduce. Okay, so elimination of commutation circuit will compensate for the additional gate drive losses. So that means efficiency in case of GTO is higher than SCR. Okay, the next difference between the two devices is reverse blocking capability. So it will be less than SCR. Always remember, SCR is the slowest device amongst all the power semiconductor switches, but at the same time it offers the highest rating, that is the reverse blocking voltage and the forward conducting current. Now due to multi-cathode structure, the spreading of the charge carriers will be faster, or we can say the conduction area will increase. So di by dt rating of GTO is higher than di by dt rating of SCR. Okay, because as we saw in the center gated SCR, if you have multiple cathodes, then what happens? More charge carriers are injected, initial conduction area increases, due to which di by dt rating increases. Which current is this? This is the anode current. It has lower size and weight. That is, it is more compact. And one thing also you can understand it in terms, as the frequency increases, the size of the device reduces. And it has lesser noise. This can be understood in the terms, and since it has lesser rating, the flux produced by the device will be lesser, so it will have less electromagnetic noise. So that is the advantages of GTO over SCR. The only disadvantage is the rating of the GTO reduces as compared to SCR. So GTO can be used where you require high frequency operation but at a lower power rating. So this is one of the most important devices of the thyristor family. The next device is called as asymmetrical SCR. Why it is known as asymmetrical? Because the forward breakover voltage is not equal to the reverse breakover voltage. Now, usually mod VBR is less than mod VBO. That is, it does not block high reverse voltage. Under high reverse voltage, it can break down and can cause conduction. So, reverse blocking capability is reduced. Okay. So, reverse blocking capability is reduced. So where we can use such a device? We can use such a device where a reverse voltage does not appear across the device. That is, whenever the supply is DC, the device will never be reverse biased. Then you can use ASCR, because then you will have to turn off the device by forced commutation technique or by means of a commutation circuit. If you are turning off an of a device by the commutation circuit, then you can control what is the reverse voltage that is applied across the device. Okay. So we will make use of commutation circuit to turn it off. But you cannot apply it in case of rectifiers because their natural commutation is preferred. That is, the nature of supply itself will support the commutation. As the supply is AC, it will reverse bias the device in the half cycle. But the voltages that are used in rectifiers are very high. So this will not be able to block the high reverse voltage and it will start conduction. So it is not preferred for the high reverse voltage applications. Okay. Now, if it cannot block high reverse voltage, that means the depletion width is less. If depletion width is less, that means stored charge carriers are also less. Okay, because when we remove the stored charge carriers, then only the depletion width is formed. If stored charge carriers are less, then depletion width will also be less. If stored charge carriers are reduced, that means the turn on and the turn off procedure becomes faster, or we can say switching time reduces. So that means T on will reduce, T off will reduce, so switching time will reduce, switching frequency increases. Hence the frequency of asymmetrical SCR is more than the symmetrical SCR. Next device is called as RCT, that is the reverse conducting thyristor. As the name suggests, it will conduct in the reverse direction, or it can be bidirectional. It can conduct in forward as well as reverse direction. Now whenever we have to make a device bidirectional, then what I told you is you have to connect a diode in anti-parallel to the SCR. So this is a anti-parallel diode. But remember, this diode is intrinsic for the case of RCT. This is not connected externally. So RCT is inherently bidirectional type of switch. Now what happens is this SCR will conduct from anode to cathode, diode from cathode to anode. So its reverse blocking capability is almost negligible. That will be same as the knee voltage of the diode. Okay. So knee voltage of the diode is the reverse blocking capability. Because as you go above the knee voltage, this diode will start to conduct. Okay. So what is the application of this? Voltage source inverter. As we will study later, voltage source inverter has a necessary condition that an anti-parallel diode is required across the device. So here anti-parallel diode is built in. You can use it for the voltage source type of inverter. Now if you compare the characteristics of SCR, then ASCR, it is not ACSR, it is ASCR and RCT, then the reverse blocking capability is highest for SCR, then for ACSR, and almost negligible for the case of reverse conducting thyristor. So that is how the breakdown voltage of different devices is compared. The next important device is TRIAC, which is also called as triode AC switch. Now it is a bidirectional as well as bipolar type of switch. As we studied in the earlier lectures. Also, the SOA is all the four quadrants. It is a fully controlled type of switch. Okay, that means both the turn on as well as the turn off of the switch can be controlled. Now TRIAC is analogous to the 2 anti-parallel SCRs, because what I told you is whenever you will connect two devices in anti-parallel to each other, then their polarity behavior will remain same. That is, a unipolar device will be unipolar, a bipolar device will be bipolar, but they become bidirectional. So a SCR by default is a bipolar and a unidirectional switch. If you combine it with another SCR which carries current in opposite direction, then this will yield a TRIAC which is bidirectional as well as bipolar. Okay, but if you take an anti-parallel diode, then the device will become unipolar and bidirectional. Remember that. Whenever an anti-parallel diode is used, the device can never be bipolar because it will not be able to block the negative voltage. Under negative voltages, the diode will turn on and it will start conduction. So a TRIAC essentially behaves as a 2 anti-parallel SCR. That is why the characteristics of the TRIAC, if you see in the figure shown, is symmetrical in the first and the third quadrant and is same as that of SCR. In SCR, in the first quadrant, characteristics were like this. This was the forward blocking mode. Then it entered forward conduction mode. And as we increase the gate current, forward breakover voltage reduced. Ig2 greater than Ig1 greater than 0. Similarly, in the reverse region, this will be the reverse blocking mode. This will be the reverse conduction mode. As you go on increasing the magnitude of the gate current, why I am not saying you are increasing gate current? Because now negative gate pulse is applied. So actually in terms of mathematics, if we see, you are decreasing the gate current, because if you are applying minus 5 ampere instead of minus 2 ampere, you have essentially reduced the gate current. But we are not interested in the sign of the gate current, rather the magnitude, because the magnitude signifies the number of charge carriers that are being injected. If you are injecting more and more number of charge carriers, then the reverse blocking voltage will reduce. So it is symmetrical in the first and the third quadrant for the case of TRIAC. Now this TRIAC is only used in medium and low power application. Okay, that means the rating of the TRIAC is much less as compared to the SCR. So what to do if I need a bidirectional and a bipolar switch for a high power application? Then I will go for this circuit where there are two anti-parallel thyristors, because the voltage and the current rating of SCR are very high. Okay, that means for high power application, the TRIAC will be replaced by the two anti-parallel SCR. And here the terminals that we have marked is MT1 and MT2, which means main terminal 1 and main terminal 2, because here we cannot define anode and cathode because current is bidirectional. By mentioning anode and cathode, it is understood that current flows from anode to the cathode, but it is not the case here. Okay, now it is also not preferred for the highly inductive load. High inductive load or high time constant, because here you have the turn off capability, or you have to make it conduct in the reverse direction. If the load has a high time constant, then it will be difficult to reduce the power current to 0 or the main current to 0 and then reverse it in the opposite direction, because it will show more opposition. So we need the low inductive loads so that the current in that can be easily reversed, or it can easily be reduced to 0. Is it fine? So, and as I told you, it is bidirectional and bipolar. The next similar device is called as diac. It is also called as diode AC switch. Here we have two anti-parallel diodes instead of SCR. Now, how does the characteristic look like? If you go on increasing the voltage up to the forward knee voltage, the current will remain 0. As soon as you go above VBO, it will enter the conduction mode, so the voltage drop will reduce. Okay, though this VBO will be small, but it will be finite. Even diode does not conduct for a voltage just greater than 0. It needs a voltage greater than the knee voltage of the diode. Similarly, in the reverse region, it will not conduct until you reach the knee voltage of the opposite diode. Suppose if one diode is like this, other is like this. So diode 1 will conduct in the forward region and 2 in the reverse region. So it will not conduct in the reverse region until you give it a voltage equal to the knee voltage of the diode number 2. Then the current will increase and it will fall on this y-axis. Okay, so that is how the characteristic of a diac looks like. If VAK is greater than VBO, then IA becomes greater than 0. If VAK is less than VBR, then IA becomes less than 0, or it starts conduction in the opposite direction. So that is how my diac behaves. Then what is the purpose of diac? Because its forward and the reverse blocking capability are very less. It is basically used in the firing circuit of the triac. How? So this is the basic circuit for the firing of a triac. Basically, we have a R and C connected in series. So we have a RC charging circuit. So what happens during the positive supply cycle? The capacitor will start charging. Now as soon as the capacitor voltage reaches the forward breakover voltage of diac, this diac will turn on, because now VAK is actually equal to VC. If it is greater than VBO, then diac turns on. If diac turns on, then current will start flowing through the diac, which is connected to the gate of triac. That means triac will get the gate pulse. Okay, and this capacitor will discharge through this path. So if you see, when triac is in the forward blocking mode, then the voltage of the capacitor is less than VBO. As soon as voltage touches VBO, the triac enters the forward conduction mode and the capacitor voltage reduces. This is my capacitor voltage which goes down. Is it fine? And as soon as capacitor voltage reduces to 0, then means capacitor has completely discharged. Similarly, in the negative half cycle, capacitor will start charging in the reverse region, and once its voltage goes below VBR, that is the reverse breakdown voltage, diac again turns on, but in opposite direction. So we get a negative gate pulse minus Ig, and capacitor again discharges. So that is the triac is in the reverse conduction region. Earlier it is in the reverse blocking region. So this is how we can fire the triac using a diac. Okay, by using a series RC circuit with a diac, we can fire the triac. So it is used in the triac firing circuit. Is it fine? So let us summarize what we covered in this lecture. We first saw the GTO, that is the gate turn off thyristor, which has an additional property. It can be turned off by a negative gate pulse. Then we saw ASCR, that is asymmetrical SCR, which has a reduced reverse blocking capability. Then RCT, whose reverse blocking capability is almost negligible and it conducts in the reverse region. Then we saw the case of triac, which is a triode AC switch, which is bidirectional as well as bipolar. And then we saw the diac, which is a diode analog of the triac and is used in triac firing circuit. So these are all the special devices from the thyristor family. Remember, diac is not from the thyristor family. Its sole purpose is to fire the triac. In the next lecture, we will look at the power transistors, that is BJT, MOSFET and IGBT. That we will cover in the next lecture. Hi guys, up to now we have seen two type of power semiconductor devices. First one was a power diode, which was a uncontrolled type of switch. Then we saw the thyristor family, in which we saw SCR, ASCR, RCT, GTO, triac. In these three switches were semi-controlled, and this switch was fully controlled. Out of this, SCR has the least frequency and it has the highest rating. And it is the most prominently type of switch that is being used in the power electronic converters. Okay. So out of all the thyristor family, the most popular switch is your SCR. So in this lecture, what we'll do is we will cover power transistors, which are also an example of fully controlled type of switches. That is, their turn on as well as turn off procedure can be controlled by application and removal of a control signal. That is, whenever you will apply a control signal at the control terminal of the device, control terminal in case of BJT is the base terminal, in case of MOSFET will be the gate terminal. So whenever you will apply a control signal, then it will turn on, and whenever you will remove the control signal, then it will turn off. That means these devices require continuous gate pulse. We cannot apply a pulse gate signal because until or till the time you apply the gate signal, then only the device is on. As soon as you remove it, it will turn it off. Okay. So these are fully controlled type of switches. So let us get started with the first type of switch, that is a power transistor or power BJT. Now, power BJT or any type of BJT has usually two configurations. One is your PNP, other configuration is your NPN. The first terminal is called as your emitter terminal. Why emitter? Because it is responsible for emitting the charges or responsible for creating the current in the device. The second is called as base, and the last one is collector. Now why collector? Because the charges that are emitted by the emitter terminal will be collected by the collector terminal. Okay, similarly here, emitter, base, collector. Usually the base is lightly doped and it has the least width. Okay, least width is for the base and it is the lightly doped region. Why we keep it lightly doped is because when the charges are emitted by the emitter, they will first enter the base region. We do not want that majority of the charges recombine in the base region. Rather, majority of charge carriers should travel and enter the collector region, where they will again become the majority carriers, and hence we have to keep the base as lightly doped as possible. This is a minority carrier type of device. Why minority carrier device? Because like in the case of PNP type of transistor, the holes will be emitted by the emitter, and once they enter the base region they will become minority charge carriers. So here whenever there is a p-n junction, the device will be called as minority carrier type of device. Also, as we have earlier studied, the BJT has a negative temperature coefficient. That is, resistance of the device decreases with increase in temperature. Due to this negative temperature coefficient, as temperature increases, resistance reduces. Now, if the resistance of the device reduces, then the current will increase, which causes the problem of thermal runaway or second breakdown. Due to this, the safe operating area of BJT first of all will be the first quadrant, okay, because it is a unipolar and unidirectional type of switch. So this will be VCE, let us say, and IC. So this will be the maximum voltage limit, maximum current limit, in between power limit, then the second breakdown limit. So this will be the due to power, this will be due to second breakdown. So that is how the safe operating area of a BJT looks like. Now in this figure I have shown the usually circuit representation of the two configurations of BJT. The first is your NPN. So remember this arrow here, it is always between the base and the ammeter terminal and it indicates the direction of current flow. Now current will always flow from P to N as the current flow direction is same as direction of holes or opposite to the flow of electrons. So if you see here, this N-type region will be emitting electrons. So electrons will be going from emitter to collector. So current will be going from collector to emitter. That means current is flowing from base to emitter and hence this arrow indicates the direction of current flow. Similarly here, holes are going from emitter to base. So that means current is also going from emitter to base. So arrow is indicated like this. Okay. Now for the case of BJT, we call it as a bipolar type of device. Now you might be confused. I told you that it is a unipolar and unidirectional type of switch. Then how I am calling it as bipolar now? See, unipolar switches and unipolar devices, these two are entirely different kind of definition. Unipolar switch means this switch can only block one polarity of voltage. Similarly, bipolar switch means it can block both polarity of voltage. But when it comes to devices, unipolar means that the current conduction is either due to holes or electrons, but not both. Either the holes will conduct the entire current or electrons will conduct the entire current, but we will not take sum of the two currents. But in a bipolar device, it means that the current is due to holes plus electron. Like in case of a BJT, due to p-n junction, wherever we will have a p-n junction, there you will get a bipolar type of device. So that means diode is also a bipolar type of device, but it is a unipolar switch. Okay, because it can only block the reverse voltage. That is what is meant by bipolar type of device. Now as with any other device, if we follow the rule of charge conservation, that is, charge cannot be created and cannot be destroyed. So amount of charge entering the device must be same as the amount of charge leaving the device. That means IE, because IE is responsible for injecting the charge, and some will combine in base region that will cause base current. Some will reach collector region, so it will be collector. So this relation is universally followed for both PNP and NPN type of transistor. Okay, that is, emitter current is same as the base plus the collector current, because whatever charges are injected from the emitter, some are recombining in the base, others are reaching the collector terminal. Now in BJT, as long as you apply base signal, this is actually the control signal, then collector current will flow. This is your power signal. Okay. So collector and emitter are actually power terminals. Base is your control terminal. So that means base current is responsible for the current flow between the collector and emitter. Hence, BJT is sometimes also called as current control device because base current controls the device characteristics. But this definition has been modified now. Now BJTs are called as voltage control device because base current is initiated by the base emitter voltage. If you apply a base to emitter voltage VBE, then only base current can flow. So the basic reason behind base current is VBE and base current is the reason behind collector current. So indirectly we can say that due to the base emitter voltage, collector current will flow in the device. Hence it can be called as the voltage controlled device. Okay. So in BJT actually we define three type of region. One is your active region in which it acts as an amplifier, and we define the gain of the current amplifier as IC upon IB, which is called as beta. The cutoff region where it acts as a off switch, here IC is taken as 0. Saturation region where it is considered as a on switch, here IC is greater than beta IB. Okay. So we are interested in only the cutoff and the saturation region, not in the active region, because we wish to use BJT as a power semiconductor switch. Now to plot the characteristics of the BJT, this is the setup. Here we have a base voltage. Let me call it as VBB. The resistance in series with the base. Then the voltage across the base emitter junction will be VB. Usually when we consider in terms of analog, VB is taken as 0.7 volt. But for a power transistor, it will be from 0.8 to 1 volt. Because what is the base emitter voltage? It is the voltage or the forward voltage of a PN junction. It will be 0.8 to 1 volt. Okay. Now, the load is connected across the collector and the emitter terminal. As I told you, these are the power terminals of the device. Okay. So here this is RL and this is your VCC. Now, the condition of different junctions for different regions of operation. Here are two junctions. One is your base emitter junction. One is your collector base, or we can say emitter base junction and collector base junction. Okay. So in cutoff region, both junctions are reverse biased, so there is no current flow. In active region, this is forward bias, this is reverse biased. Then in saturation region, both junctions are forward biased. And in reverse active, this is your reverse biased, this is my forward biased. Okay. What is meant by reverse active is, if the transistor acts as an amplifier in the active region, then in the reverse active region it will act as a attenuator. That is, it will decrease the signal amplitude or the gain will be less than 1. Now if you see here, what kind of transistor it is? NPN. Okay. So here what we have done is, we have forward biased the base emitter junction. How? Because we have applied a positive voltage to P and the ground to the N terminal. This is also called as common emitter configuration because emitter terminal is common between the input and the output. Input is applied across base emitter, output across the collector emitter. So this is the common emitter configuration where base emitter junction is forward biased by a positive voltage and collector base junction is reverse biased because we are applying a positive voltage at the collector, which is actually N terminal. Okay, so that is how we have reverse biased the collector base junction. So that is, we are operating in the active mode. Now as I told you, for the switch operation we operate in either the saturation or the cutoff mode. Then why are we operating in the active mode? Because whenever we wish to plot the characteristics, we will always operate in the active mode of operation. So here if you see, the input characteristics are the characteristics between IB and VB. Here for different VCE, if you see, if we increase VCE, then for the same current VB increases, or we can say for the same voltage IB increases. If VCE increases, so if we keep the voltage same like this, okay, then as VCE increases, IB reduces. Now why does this happen? Let me tell you why IB is decreasing with increasing VCE. If we apply KVL in this loop, then VCC minus ICRL is equal to VC. Now as VC increases, IC reduces, and IC is equal to beta IB, hence IB also reduces. But there is negligible effect of change in the collector to emitter voltage on the base current. There is not much effect. Okay, so these are the input characteristics of the BJT. How does the output characteristic look like? Here, if you keep base current as 0, that is, we haven't applied any control signal. So the switch will be in the off state. So this is my cutoff region. If IB is 0, then IC is also 0. So it is the cutoff region. And if you apply base signal, if you keep on increasing the base current, as IB increases, IC also increases. So this initial region is called as your saturation region. Here collector to emitter voltage is VCE set, which is low. Okay. In signal transistor we take VCE as 0.2 volt in saturation region. Okay. And if you keep on increasing the base current further, then the collector current almost becomes constant at a fixed value. But we cannot go beyond this value because the power dissipation in the switch. In BJT, the power is actually VCE into IC, because the power terminals are the collector and the emitter terminals. So what will be the power dissipated in the switch? The voltage across the switch into the current multiplied current of the switch, that is VCE into IC. So if you go beyond a certain point, then breakdown will occur. Okay, that is, there will be a flood of charge carriers, due to which the current will increase exponentially and the device will break down or device can get damaged. So we cannot go beyond this point. So this is the essential difference with the signal, because when we talk about the signal transistor, then we do not show any breakdown strength, or we do not show any point or any limit on the characteristics, because there the power dissipation is not so high as to cause the damage to the transistor, because their collector current is in the range of milliampere and base current in the range of microampere. Here we will have base current in the range of amperes and collector current in the range of hundreds of ampere. So at high current it can damage the transistor. Okay. So remember, whenever we will use the BJT, we will make use of this cutoff and this saturation region, but not this active region. In active region actually, collector current is fixed at beta IB. So this is actually the value of beta IB. That means in saturation region, IC is less than beta IB. It is actually not equal to the beta IB. So please make a correction. I think in earlier slide I told you that IC is greater than beta IB. But remember, IC will be less than beta IB for the case of saturation region. So there I told it by mistake that it should be greater. But actually this is the actual condition. So we define a current called as IBS, that is the base saturation current. It is the minimum base current required to saturate the transistor. Now ICS will actually be equal to beta IBS. But in saturation region, usually collector current is less than the base current. Now if we apply KVL in the outer loop or in the power terminal, VCC minus VCE will be ICS into RL. This is for the case of saturation. That means ICS will be VCC minus VCE by RL. This is the collector current under the saturation condition. So IBS will be equal to actually ICS by beta. Okay. But as I told you, IC is less than beta IB. That means IB is greater than ICS upon beta. That means IB is greater than IBS. The ratio of IB upon IBS is called as overdrive factor. Now why it is called as overdrive factor? Because it means how much additional base current you are supplying more than the minimum base current required for saturation. That is, you are overdriving the transistor. That much base current is not necessary. You are applying more than the required. So if overdrive factor is greater than 1, then transistor is in saturation region. Is it fine? It indicates the ratio of actual base current to the minimum current required for the saturation region. Now let us look at the switching characteristics of the transistor. Here we will apply the base voltage or the base current. So base voltage will cause base current, and whenever base current will be applied, the collector current will start rising, and as it reaches the maximum value, this will be the turn on time of transistor. Similarly, the collector to emitter voltage will fall to a low value in the turn on time. Then they will stay like this. Now to turn off the device, you can keep IB equal to 0. But then the stored charge carriers will take a long time to deplete. If you want to control the turn off, or if you want to control the turn off time, then you will apply a negative gate signal or the negative base current. If we apply negative base current, then charge carriers will move in the opposite direction and the charge carriers will be removed from the device. Stored charge carriers can be easily removed if we take the negative gate current or negative base current. So here we apply a negative base current. So up to this point, this is the storage time in which the stored charge carriers are removed. After that, even if you reduce the base current to 0, the transistor current will itself fall to 0 because you have removed the stored charge carriers. That is why we just need to apply the negative base current until the stored charge carriers are removed, because once the stored charge carriers are removed, the transistor will itself turn off. So the time taken to remove the stored charge carriers is called as the storage time. And then the time taken by anode current to fall to a low value will be your fall time. Okay, so that is your turn off time. Total turn off time here can be written as fall time plus storage time. So this is not the turn off time, rather this is your turn off time. Is it fine? And if you want, you can also include the tail time, in which the anode current in which the collector to emitter current will fall from 10% to the 0%. Is it fine? So here sometimes we draw approximate characteristics for this BJT. Now how the approximate characteristics look like for the voltage? Voltage falls linearly to 0, then increases linearly to a higher value. Similarly, current will remain 0, then it will increase to a high value, stay at that high value, then it will decrease to a 0 value. This is your IC, this is your VC. So for such a waveform, this will be your T on, this will be your T off. In the lecture that we discussed the conduction losses We derived the conduction as well as switching losses. In this, we derived the switching loss for such a waveform as Vc Ic by 6 T on plus T off. That is the energy loss during the switching. So what is the switching power loss? It is frequency into switching energy. Okay, so that is how the switching characteristics of a BJT look like. Is it fine? Next, let us move on to the power MOSFET. First of all, what is the meaning of the term MOSFET? MOSFET means metal oxide semiconductor field effect transistor. Why metal oxide semiconductor? Because here, if you see, this is your metal terminal. Then this is oxide, which acts as an insulator. Then this is semiconductor. So here we have a metal oxide semiconductor junction, hence MOS. Why field effect transistor? Because if you have applied a oxide or an insulating layer, then current cannot flow from the gate terminal into the semiconductor. This metal actually refers to the gate. So current cannot flow from gate to the semiconductor. Only the electric field can pass through the oxide, which acts as a dielectric. So it is run by means of field. Hence the name field effect transistor. Now power MOSFET has three terminals. One is your gate terminal, one is your drain terminal, other is your source terminal. Where this gate terminal is actually the control terminal, and these other two terminals are the power terminals where we will apply the actual voltage and the current. Now here I have shown the actual structure of a power MOSFET. If you see, at the bottom we have a drain region, which is N plus region, drain. Then we have a N substrate. This is the body, or it is the drift region. As I told you in the power diode, what is the purpose of drift region? It is to increase the breakdown voltage of the device. But it also increases the on-state resistance. Now, here we have these 4 N plus regions. These are my source regions. So, how does a power MOSFET works? Here, the control signal is applied at the gate terminals, whose sole purpose is to enable the current flow from the drain to the source, or to enable the charge carriers to flow from source to the drain. That is how the current will flow in case of a power MOS. So it is the duty of gate to let us say to induce the current between the drain and the source terminal. Is it fine? Now how does the gate do that? If we apply positive voltage to the gate, then it will cause electric field. How will the electric field look like? Electric field will be like this, away from the positive terminal. Now as we know, electrons will move in the opposite direction. So how will the electrons move? They will move upwards. Now when electrons move upwards, they will be accumulated into this region. Since this region is actually P region, so electrons will accumulate inside this P region here. So this entire path becomes N. This is N plus, then N minus, then also the electrons. So between source and drain, the entire path is your N region. Hence it acts as a N-type semiconductor. When it acts as a N-type semiconductor, then it acts as a resistance. Okay, because a semiconductor material, whether it is just P-type or N-type, it acts as a resistance. It is only when we have a PN junction that the device properties begin to change. That is why I told you MOSFET is modeled in the on state as a resistance RD. Is it fine? Because the entire path between the drain and the source consists of N-type material which acts as a resistance. So what is the duty of the gate terminal? Its duty is to induce the charge beneath the gate terminal so that current can flow between the source and the drain. This induced charge is also called as channel. So duty of gate terminal is to induce the channel between the source and the drain. Is it fine? Now, in MOSFET, we have two type of MOSFET, enhancement type and depletion type. In enhancement type, the channel will be formed due to application of gate voltage. But in depletion type, we already have the channel existing in the device. So if you have already a channel existing in the device, as soon as you apply a potential difference between the drain and source, the drain current will begin to flow. That means the turn on of the device is not in my control. So in power MOSFETs, we will use only the enhancement type of MOSFET, where I can control the turn on and turn off of the device. Okay. Now why MOSFETs are advantageous? Because they have high input impedance and low output impedance. Okay. And also MOSFETs. Now if you see here, the entire path between the drain and source is N region. So there is no PN junction formed in the path of current. Since no PN junction is formed, that means it is a majority carrier device. Also, if you see in this particular example, the entire current conduction is due to N type or due to electrons. So this is a unipolar device. Okay. So MOSFET is a unipolar switch as well as a unipolar device. Unipolar device because only either the electrons or holes will conduct. Because in MOSFET we have PMOS and NMOS. Okay, in PMOS actually the drain and the source regions are P plus as well as channel is P. In NMOS drain and source are N plus and the channel is N. Okay, so here electrons will conduct, here holes will conduct. So it is a unipolar device. Also, since it is a majority carrier type of device, there are no stored minority carriers. So no need to remove the stored minority carriers and hence the switching time are faster as compared to BJT. That means on time and off time are low, due to which switching time is low, or we can say switching frequency is high. Now this is the standard representation of a MOSFET in which three terminals gate, drain and source are shown. This broken line here indicates this is enhancement type. Okay. Because there is no channel between the drain and source. If you apply a gate potential, then channel will be formed and current can flow between the drain and the source terminal. Okay. So this is the basic working of the MOSFET. Now let us look at the transfer characteristics of the MOSFET. When we talk of input characteristics, then we show the ID VGS. This is actually also called as transfer characteristics, because here the input is VGS and the output is ID. So actually one voltage is being considered at the input and the current is taken as output, so it will be the transfer characteristics. In MOSFET we define three regions of operation: linear or ohmic region, cutoff region and saturation region. In cutoff region actually the gate to source voltage is less than the threshold voltage. If it is less than the threshold voltage, then MOSFET will not be able to work. In linear or ohmic, it is greater than threshold, but here drain to source is less than VGS minus VT. In saturation, VGS is greater than VT and drain to source voltage is also high, that is greater than VGS minus VT. So we are interested in only cutoff and the saturation region for the device operation. Now here if you see ID is 0 up to VT, so this is your cutoff region. Then as VGS increases, IDS increases, and these are multiple curves which are shown for higher value of VDS. That is, ID increases with increase in VGS as well as increase in VDS. So these are the transfer characteristics which have been drawn by the use of this circuit. Here we have applied a positive voltage between the gate and source and a positive voltage between the drain and the source with the load resistance. Since these are the power terminals, here we will show the load resistance. This is the control terminal, so we will show a small resistance, that is Rg. Looking at the output characteristic will make it more clear why we call at these linear and the saturation region. So here, whenever VGS is less than VT, current will not be able to flow. This is your cutoff region. So now if you take VGS greater than VT, that is VGS1, then VGS2 is greater than VGS1, and VGS3 is greater than VGS2. So this is actually VGS2. So as you increase VGS, the drain current will increase. Now this is the active region, or this is your saturation region. In this we do not define the active region. Why saturation? Because even with increase in VDS, the ID saturates and it becomes constant. It does not change. And this is your ohmic or the linear region, because ID varies almost linearly with VDS. Okay, this is the approximate relation where ID varies linearly with the VDS, but once it becomes constant, it is termed as the saturation region. So we will operate in the cutoff and the saturation region, and this is we will show the breakdown limit. Remember, there is no second breakdown. So if there is no second breakdown, that means the only breakdown is due to the average power dissipation. Is it fine? Next we move on to the last type of transistor, that is IGBT. Here we make one change, that is instead of the drain having N plus region, it is now P plus collector. So whatever was the source is now called as emitter, but gate will remain as gate. IGBT means insulated gate bipolar transistor. As the name bipolar suggests, that means conduction will be due to holes and electrons, or we can assume there will be a PN junction in the path of current. Insulated gate means the gate will be insulated from the semiconductor region by means of an insulator. Okay, this is my insulator. Now what will happen is, whenever you will apply a positive gate voltage, N channel will be induced due to positive gate voltage will attract the electrons. Now when the current will flow from collector to emitter, it is essentially flowing through a PN junction. Okay, because it is P, then N channel, then N plus. So it is flowing through a PN junction instead of a N type of semiconductor. Hence it is given the name as the bipolar transistor. Now what is the advantage of IGBT? It combines the advantages of MOSFET and BJT. Okay, and it has no signal counterpart. It is only defined for the power electronics, not for the analog electronics. This is the basic representation of IGBT, where we have a gate as a control terminal, collector and emitter as the power terminal. This space between these two indicates the presence of a insulator. That gate is not connected to the collector or the emitter terminal. Okay, so here there is only one essential difference, that N plus drain is replaced by the P plus collector. Rest of the process remains the same. So if we wish to plot the transfer characteristics, we will apply a positive gate voltage with a resistance Rs, and we will apply a positive collector voltage with a resistance R. So as you increase the gate to emitter voltage, the collector current will increase. Okay. As we increase the gate to emitter voltage, more charges will be induced in the channel. If more charges are induced, then it will easily cause the flow of current between the collector and emitter. Similarly, we can plot the output characteristics. Here, these are similar to the case of MOSFET. But here, we will define the active region instead of the saturation region. This is active. This is your ohmic or the linear region. And this is my cutoff region. So we will operate in the active region as well as the cutoff for the transistor operation. Okay. So here cutoff means switch is off. Active means switch is on. Is it fine? We will not operate in the linear or the ohmic region. Now finally let us compare the characteristics of IGBT, BJT and MOSFET. Now BJT is actually current control device, or it is controlled by VIB, but you can also call it as voltage control because it is controlled by VB. Now MOSFET is controlled by VG, so it is a voltage control device. IGBT is also controlled by VG, it is a voltage control device. Now it is a bipolar device because current conduction is due to both electrons and holes. It is unipolar. Current conduction is due to either holes or electrons. IGBT is bipolar. Okay. It has Z input as low input impedance. Z input is high input impedance. Also here Zn is high. Why high input impedance is required? To eliminate the loading effect. What is loading effect? Whenever the second system in cascade draws current from the first system, it is called as loading effect, which is undesirable. Okay, we want that second system should only derive the voltage input from the first and not draw power from the first system, or it should not draw any current. Because if it wants to draw power, it must draw from the supply and not from the output of the first system. Here R on is low due to conductivity modulation. Here R on is actually high. Due to the drift region, resistance increases, but since there was no PN junction being formed, there is no conductivity modulation. Okay, if there is no conductivity modulation, that means R on will remain as high. Here R on is low. Now if on-state resistance is low, what are the impact? The on-state voltage drop will be low as well as on-state conduction loss will be low. So BJT and IGBT have low on-state or the conduction losses, but MOSFET has high losses. Okay, it has higher switching loss. It has lower switching loss. It also has lower switching loss. So that is how IGBT combines the advantages of BJT and MOSFET, that it has a lower switching loss as well as a low conduction loss. Okay. It has a negative temperature coefficient. It has positive temperature coefficient. Positive temperature coefficient. That means the resistance will increase with increase in temperature. What is the impact? That these devices can be used for parallel operation, whereas BJT has a second breakdown problem, so it will not be used for parallel operation. So second breakdown problem occurs only in BJT and not in case of MOSFET and IGBT. Okay. So here we have second breakdown. Here no second breakdown. Also, due to higher conduction losses, MOSFET will have a lower rating, whereas BJT and IGBT will have higher rating. So what are the ratings? BJT will have a rating of 120 volt, then 800 ampere, but frequency will be low because of higher switching losses, 10 to 20 kilohertz. MOSFET has low rating, 500 volt, only 140 ampere, but frequency is high, that is 1 megahertz. IGBT has high rating as well as high frequency, that is 50 kilohertz. But still its switching frequency is less than MOSFET. So MOSFET is the fastest device. And remember, due to second breakdown, BJT is not recommended for parallel operation, whereas MOSFET and IGBT can be used in parallel operation. Also, if you see one thing, in case of IGBT, how that body diode is being formed. This is the P region and this is the N region. So here there will be a diode. And this diode will conduct in the opposite direction like this. But current is flowing like this. So that is why we show an anti-parallel diode with IGBT and MOSFET. In MOSFET also, if I show you, due to this P-type region, this is your parasitic diode or the body diode. Okay. it will carry current downwards, but actually the current is flowing like this. So hence we show a body diode in parallel with MOSFET and IGBT, but there is no such diode in case of BJT. Is it fine? So let us summarize what we covered in this lecture. We first saw power BJT. We saw the construction, the operation and the switching characteristics. Then we saw power MOSFET. We saw that it is a majority carrier type of device. It is a unipolar device and it has higher switching frequency and higher conduction losses. Then we saw IGBT, insulated gate bipolar transistor, which combined the advantages of MOSFET and BJT, and it is also a bipolar type of device and it has lower conduction losses as well as lower switching losses. In terms of speed, MOSFET has the highest speed, then it is IGBT, then it is BJT, and even SCR will lie at the least. SCR has the highest rating but the lowest frequency. In terms of rating, SCR has the highest rating, then the rating will be lying for IGBT, then for the case of BJT, then for the case of MOSFET. Okay, this will be the order of rating here, frequency. So this is all about your power semiconductor type of devices. Mostly the questions that are asked from these power transistors are theory concepts. So you have to essentially remember the differences that we have studied in IGBT, MOSFET and BJT. Okay. So in the next chapter we will study about the rectifiers.